In the frozen vacuum of space, 13 billion light-years from Earth, something impossible is staring back at us. The James Webb Space Telescope has peered deeper into the cosmic abyss than any instrument before it, and what it found defies every law of physics we thought we understood. Ancient galaxies that shouldn't exist, black holes older than time itself, signals from the edge of reality that suggest our universe might be rotating inside something far larger and stranger than we ever imagined. Something is terribly wrong with the universe itself. For decades, scientists believed they understood how fast our cosmos was expanding. The Hubble Space Telescope gave us one measurement. Mathematical models predicted another. Everything seemed to fit together like pieces of a cosmic puzzle. Then James Webb looked deeper than anyone had ever looked before, and the puzzle exploded into 1,000 fragments. The universe is expanding at two completely different speeds depending on where you measure it. Think of it like a balloon being inflated, but the top half stretches twice as fast as the bottom half. This should be impossible. The laws of physics demand that expansion happens uniformly across all of space. Webb confirmed what astronomers feared most. When they measured the expansion rate using distant stars called Cepheid variables, they got one number. When they calculated it using the cosmic microwave background radiation, they got a completely different number. The difference isn't small. We're talking about a discrepancy so massive that it suggests our fundamental understanding of reality is wrong. Scientists call this the Hubble tension. But that name doesn't capture the true horror of what we're dealing with. This isn't just a measurement error or a calibration problem. After studying over 1,000 Cepheid stars across 5 separate galaxies stretching 130 million light-years into space, the contradiction remains. The implications are staggering. Either our models of how the universe works are completely broken, or there's some unknown force tearing reality apart. Dark energy, the mysterious substance that drives cosmic expansion, might be behaving in ways we never imagined. Some regions of space could be expanding faster than others, creating cosmic rifts that challenge everything we know about space-time. Adam Rees, the lead researcher who discovered this crisis, put it bluntly: with measurement errors ruled out, what remains is the real and exciting possibility that we have fundamentally misunderstood the universe. The word exciting feels wrong when you consider what this means. If our basic understanding of cosmic expansion is incorrect, then our calculations about the universe's age, size, and ultimate fate are all suspect. Webb's unprecedented precision has removed any doubt about the measurements. Both the telescope and Hubble are detecting the same impossible contradiction. The universe is expanding, but it's doing so in a way that breaks the laws of physics as we understand them. This discovery alone would be enough to shatter cosmology textbooks. But Webb was just getting started. As the telescope continued its survey of deep space, it began finding objects that shouldn't exist, behaviours that defy explanation, and phenomena that suggest our reality is far stranger and more dangerous than we ever imagined. The expansion crisis was only the beginning of a series of discoveries that would force scientists to question everything they thought they knew about the cosmos. When James Webb pointed its infrared eyes toward a seemingly empty patch of sky near the Big Dipper, astronomers expected to find tiny baby galaxies stumbling through their first billion years of existence. Instead, they discovered 6 massive, mature star systems that shouldn't have had time to grow so large. These galactic giants contain nearly as many stars as our own Milky Way, but they formed when the universe was only 3% of its current age. Picture trying to grow a full-sized oak tree in just 3 months. That's essentially what these galaxies accomplished on a cosmic scale. Star formation takes time. Gravity needs millions of years to pull together enough gas and dust to ignite nuclear fusion. Yet these 6 systems somehow fast-tracked their development, becoming galactic titans while the universe was still in its cosmic infancy. The discovery happened almost by accident. Astrophysicist Erica Nelson was examining postage stamp-sized sections of Webb's deep field images when she spotted several fuzzy red dots that looked impossibly bright. Red light in astronomy usually means old light stretched by the universe's expansion during its long journey to Earth. But these objects were both ancient and blindingly luminous, a combination that defied explanation. Each of these monster galaxies contains between 10 billion and 100 billion stars. To reach such enormous sizes so quickly, they would have needed to form hundreds of new stars every single year for hundreds of millions of years. Our Milky Way, by comparison, creates only about 2 new stars annually. These ancient systems were stellar factories operating at production rates that modern physics says should be impossible. The team has informally nicknamed these objects universe breakers because they threaten to break our understanding of how cosmic structures form. According to every simulation and model scientists have created, matter in the early universe should have clumped together slowly and methodically. Small structures would gradually merge to form larger ones over billions of years. These 6 galaxies throw that entire timeline out the window. They suggest that the early universe was capable of organization and complexity that cosmologists never imagined possible. Either there's a completely unknown mechanism for rapid galaxy formation, or our fundamental assumptions about cosmic evolution are catastrophically wrong. The discovery raises terrifying questions about dark matter's role in early cosmic development. If galaxies could grow this massive this quickly, it means dark matter was clumping together and pulling in regular matter at rates far exceeding current predictions. The invisible scaffolding that shapes our universe might be far more violent and unpredictable than we realized. Joel Leger, one of the astronomers studying these objects, captured the magnitude of the problem perfectly. We looked into the very early universe for the first time and discovered something so unexpected that it creates genuine problems for science. But confirming whether these are real galaxies required additional observations with Webb's spectrograph, and what those follow-up studies revealed would prove even more disturbing than anyone anticipated. Deep in the early universe, James Webb discovered something that shouldn't exist according to every theory of black hole formation. Sears is a supermassive black hole with virtually no galaxy surrounding it. It's essentially naked, drifting through space without the typical host of billions of stars that normally accompany such massive objects. Most supermassive black holes sit at the centers of galaxies like cosmic anchors, surrounded by spinning disks of stars, gas, and dust. They form a symbiotic relationship with their galactic hosts, growing together over billions of years through a delicate dance of gravity and star formation. But Sears breaks this pattern completely. This monster with the mass of 50 million suns is wandering through space completely alone, rewriting the history of the cosmos. The discovery challenges everything astronomers thought they knew about black hole formation. Traditional models assume that supermassive black holes grow gradually at the centers of galaxies, feeding on gas and dust over billions of years. But Sears appears to have formed through a completely different process, one that created a massive black hole without simultaneously creating a galaxy around it. Some researchers suggest that Sears might be a primordial black hole, an ancient monster that formed in the first few 100 million years after the Big Bang through processes we don't yet understand. If this theory is correct, it means the universe was capable of creating supermassive black holes before the first galaxies even existed. These primordial monsters would have been sitting in the dark for hundreds of millions of years, waiting for the universe to evolve enough to provide them with food. The implications are staggering. Primordial black holes could explain how supermassive black holes grew so massive so quickly in the early universe. They had a head start of hundreds of millions of years, allowing them to reach enormous sizes before the first galaxies even began to form around them. But this scenario raises even more disturbing questions. If primordial black holes were common in the early universe, they might still be out there today, invisible and undetected. Some could be wandering through our own galaxy, ancient relics from the universe's violent birth that predate every star we can see. These primordial monsters represent a fundamental shift in our understanding of cosmic evolution. Instead of a universe that gradually built complexity from simple beginnings, we might be looking at a cosmos that was born with powerful, massive objects already embedded in its structure. But Webb's surveys revealed something even stranger scattered across the ancient universe. Astronomers call them the little red dots, and they might be the most mysterious objects ever discovered. These crimson specks appear throughout Webb's deep space images, glowing with impossible brightness from the universe's earliest epochs. Each one is a puzzle that challenges our understanding of how cosmic structures can form. The little red dots are both incredibly compact and extraordinarily luminous. They're roughly the size of our solar system but outshine entire galaxies. This combination shouldn't be possible. Normal galaxies spread their light across billions of stars distributed over hundreds of thousands of light years. The little red dots concentrate similar amounts of energy into regions that would fit inside the orbit of Neptune. If they're galaxies, they're unlike any that exist today. The objects are so bright that they force scientists to reconsider how galaxies could have formed in the early universe. Traditional models assume that the first galaxies grew slowly, accumulating matter through gravitational collapse over hundreds of millions of years. The little red dots suggest that some process was creating massive luminous structures much more rapidly than current theories allow. But here's where the mystery deepens. When astronomers try to determine exactly what's producing all this light, the answers don't make sense. Some of the objects appear point-like, suggesting they might be powered by supermassive black holes rather than distributed star formation. Others show evidence of extended structure, indicating they might be genuine galaxies undergoing extraordinarily rapid star formation. The most disturbing possibility is that these objects represent a completely unknown phase of cosmic evolution. During the universe's first billion years, physical conditions were drastically different from today. Matter was denser, dark matter interactions were more frequent, and the cosmic web of large-scale structure was still forming. Perhaps these conditions allowed for types of object formation that can't happen in the modern universe. Some of the little red dots show evidence of extremely high-energy processes. They emit X-rays, ultraviolet radiation, and infrared light in patterns that suggest violent, chaotic energy production. Whatever is powering these objects is operating under extreme conditions that push the boundaries of known physics. The objects also appear to be distributed randomly throughout space, rather than clustered in regions where early galaxy formation was expected to occur. This random distribution suggests they might represent a fundamental property of the early universe, rather than rare, isolated phenomena. Bingjie Wang, the graduate student leading the research, emphasizes that even if only a few of these objects are confirmed to exist in the early universe, they will force scientists to modify existing theories of galaxy formation. The sheer number of mysterious objects Webb has found suggests that our understanding of cosmic evolution during the universe's youth is fundamentally incomplete. The little red dots represent perhaps the most significant challenge to cosmology that Webb has discovered. But their mystery pales in comparison to what the telescope found when it looked at the large-scale structure of the universe itself. Galaxies across vast regions of space are spinning in synchronized patterns that suggest the universe might have been born rotating. In what may be James Webb's most mind-bending discovery, astronomers have found evidence that galaxies separated by millions of light years are rotating in coordinated patterns. This cosmic choreography shouldn't be possible. Galaxies form independently from local clouds of gas and dark matter. Their rotation direction should be random, scattered across the sky like leaves falling from a tree. Instead, Webb has detected a subtle but unmistakable alignment. Across enormous volumes of space spanning hundreds of millions of light years, galaxies show a preference for spinning in similar directions. The effect is subtle, but statistically significant enough that it can't be explained by chance. Some regions of the universe appear to have a preferred rotational axis, as if the cosmos itself is turning on some hidden spindle. The implications are staggering. If galaxies separated by such vast distances are coordinating their rotation, it means some form of connection or correlation existed when they formed. But standard cosmological models predict that regions of space this far apart should have no way to influence each other. They're beyond each other's causal horizons, meaning no signal or force travelling at the speed of light could have connected them since the Big Bang. Some unknown force or field must be operating on the scales larger than anything scientists have previously considered. A rotating universe would have different physical properties than the static cosmos described by standard models. Space and time themselves might have preferred directions, creating asymmetries in physical laws that could affect everything from particle physics to the ultimate fate of the universe. The discovery also raises questions about dark energy, the mysterious force driving cosmic expansion. If the universe has a preferred rotational axis, dark energy's effects might vary depending on direction, creating a cosmos that expands faster in some directions than others. This could explain some of the anomalies Webb has found in cosmic expansion rates. Perhaps most unsettling is what a rotating universe suggests about our place in the cosmic hierarchy. If our universe is spinning inside a larger structure, it implies that reality extends far beyond the observable cosmos. We might be living inside just one component of an incomprehensibly vast multiverse where entire universes rotate like galaxies within some higher dimensional space. The coordinated galaxy rotations and the strange behaviour of cosmic expansion suggest we might be living inside a black hole within a larger universe. The most terrifying possibility raised by James Webb's discoveries is that our entire observable universe might be the interior of a massive black hole existing within a larger cosmic structure. This black hole cosmology theory explains several of Webb's most puzzling observations. The evidence begins with the galaxy rotation patterns Webb discovered. Galaxies separated by millions of light years are spinning in coordinated directions, a phenomenon that should be impossible unless the entire universe has a preferred rotational axis. In black hole cosmology, this coordination would result from our universe inheriting the angular momentum of the parent black hole that contains us. The theory suggests that what we call the Big Bang was actually our universe crossing the event horizon of a massive black hole in a higher dimensional space. From our perspective inside the black hole, this crossing appears as cosmic expansion, but from the perspective of the larger universe, we're falling toward the black hole singularity in a process that will take infinite time due to gravitational time dilation. This scenario explains the accelerating expansion of space that we attribute to dark energy. As we fall deeper into the parent black hole, space-time curvature increases, creating the illusion that expansion is accelerating when we're actually approaching regions of more severe gravitational distortion. Webb's discovery of primordial black holes that predate star formation also fits the black hole cosmology model. These ancient monsters could be smaller black holes that existed in the parent universe before we crossed the event horizon, appearing in our cosmic history as primordial objects that formed before normal matter could collapse into stars. The coordinated galaxy spins that Webb observed make perfect sense if our universe inherited rotational momentum from a spinning parent black hole. The galaxies aren't mysteriously coordinating their motion. They're all participating in the same cosmic rotation that was imprinted on space-time when our universe formed. Even the expansion rate contradictions that have puzzled astronomers fit the black hole cosmology model. Different measurement techniques might be detecting different aspects of our motion through the curved space-time inside the parent black hole. If black hole cosmology is correct, it means that everything we can observe, from the cosmic microwave background to the most distant galaxies, exists within the event horizon of an incomprehensibly massive black hole. We would be forever separated from the larger universe that contains us, unable to communicate with or affect anything outside our cosmic prison. The theory also suggests that black holes throughout our universe might contain entire universes of their own, creating a nested hierarchy of cosmic structures where each black hole serves as a gateway to a complete cosmic realm with its own physics, evolution, and potentially life. This possibility transforms our understanding of cosmic significance and our place in the broader structure of reality. At the centre of our Milky Way galaxy, hidden behind clouds of dust and stars, lies something we cannot see with our eyes, but which has the mass of millions of suns. This mysterious object is called Sagittarius A star, and it's a supermassive black hole. Unlike the monsters powering distant quasars and active galaxies, Sagittarius A star barely makes a peep. But its silence is misleading. For a long time, even after people began building telescopes and studying the stars with scientific tools, the centre of the Milky Way remained hidden. Astronomers could map parts of the sky, track planets, and chart the motion of stars. But something was still in the way. Whenever they turned their instruments toward the thickest part of the Milky Way, toward the constellation Sagittarius, they ran into a wall. This area, now known as the Galactic Bulge, is one of the most crowded regions in the entire Milky Way. It is a huge central swelling made of hundreds of billions of stars. From Earth, it lies in the direction of the galactic centre, but seeing through it is not easy. When people look up at the Milky Way with the naked eye, they see a pale band stretching across the night. It looks almost like a faint cloud, but that band isn't made of cloud or mist. It's made of stars. That glow gets brightest near the centre of the Milky Way, but along with the brightness comes something else. darkness. This darkness is not the absence of stars, it's the presence of dust. All across the galaxy, floating between stars are clouds of interstellar dust. These clouds are made of tiny particles, bits of carbon, ice, and rock left over from older stars and drifting slowly through space. While these particles are small, they're spread out over such huge distances that they can block light, especially visible light, the kind our eyes and early telescopes can see. That's the key problem. For most of history, telescopes worked only in visible light. They were built like giant eyes, collecting light from stars and focusing it into images. But visible light is easily blocked. The breakthrough came with infrared technology. Unlike visible light, infrared radiation can pierce through dust clouds. In the 1970s and 80s, astronomers began using infrared detectors to peer through the galactic bulge. What they found was extraordinary. At the very centre of the Milky Way there was a powerful radio source. Scientists named it Sagittarius A star. At first they weren't sure what it was. The signal was strong but compact, coming from a region smaller than our solar system. Over time, as telescopes improved, astronomers began tracking individual stars near this mysterious radio source. What they discovered would change our understanding of the galaxy forever. The stars closest to Sagittarius A star were moving at incredible speeds. Some complete an orbit around the invisible centre in just a few years, reaching velocities of several thousand kilometers per second. This kind of motion could only be explained by an enormous concentration of mass, but there was nothing visible at the centre. The only explanation that fit the data was a supermassive black hole. By carefully measuring the orbits of these stars, scientists calculated that Sagittarius A star has a mass of about 4 million times that of our Sun. That's enormous by stellar standards, but relatively modest for a supermassive black hole. Some galaxies host black holes billions of times more massive than our Sun. Still, 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun represents a gravitational force beyond everyday comprehension. The evidence grew stronger with each passing year. In 2020, astronomers watched as a star called S2 made its closest approach to Sagittarius A star. The star whipped around the black hole at nearly 3% the speed of light, its path bent by the immense gravity in ways that matched Einstein's predictions from general relativity. These observations confirmed not only the presence of the black hole, but also that our understanding of gravity holds true, even in the most extreme environments. By the early 2000s, the scientific community had reached a consensus. The Milky Way, like most large galaxies, has a supermassive black hole at its core. This wasn't just theory, it was backed by decades of careful observation and mathematical modelling. In 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for their work proving the existence of Sagittarius A star. But proving the black hole exists and understanding what it does are two different things. Sagittarius A star influences the entire galaxy in ways both subtle and profound. Its gravity shapes the orbits of stars within thousands of light years. It acts as a kind of cosmic anchor, holding the central bulge together and possibly influencing the formation of the Milky Way's spiral structure. Yet compared to black holes in other galaxies, Sagittarius A star is remarkably quiet. Many supermassive black holes are active, consuming huge amounts of material and producing blazing jets of energy that can be seen across cosmic distances. Our galactic centre is currently in a low activity phase, feeding only occasionally and producing brief flares in radio, infrared, and X-ray wavelengths. This quietness makes it harder to study in some ways because it doesn't have the bright, obvious emissions that active galactic nuclei produce. Yet it also makes it an ideal laboratory for studying the black hole itself without interference from the chaos of extreme feeding events. Scientists have even captured an image of Sagittarius A star, or more precisely, an image of the glowing material orbiting it. In 2022, the Event Horizon Telescope collaboration released the first image of our galaxy's central black hole. It showed a ring of superheated gas surrounding a dark central shadow, the black hole's event horizon silhouetted against the bright accretion disk. The image matched theoretical predictions with remarkable accuracy, providing visual proof of the monster lurking at the heart of the Milky Way. Sagittarius A star weighs in at about 4 million times the mass of our Sun. That sounds enormous, and it is, but in the realm of supermassive black holes it's actually on the smaller side. Take the black hole at the centre of the galaxy M87, the same one famously imaged by the Event Horizon Telescope in 2019. This black hole is about 6.5 billion solar masses, over 1,600 times the mass of Sagittarius A star. It's big enough to fit our entire solar system, including the Oort cloud, well within its event horizon. Despite its enormity, M87's black hole is not even in the running for the largest ever found. Then there's Holmberg 15A star, a central black hole in a galaxy cluster more than 700 million light-years away. This one has been estimated to weigh in at around 20 billion solar masses. And then there's TON 618. This monster is one of the largest known black holes in the universe, and it makes Sagittarius A star look like a pebble beside a skyscraper. Estimates place TON 618's mass at around 40 billion times that of our Sun. To put that into perspective, you could line up over 10,000 black holes the size of Sagittarius A star before you'd match its mass. TON 618's event horizon is so vast that light would take about a week to travel across it, compared to about 24 seconds for Sagittarius A star. The scale is beyond everyday comprehension. What's interesting is that even though these black holes are so much bigger, they may not be dramatically more dangerous in their immediate environments. A black hole's pull only becomes overwhelming close to it. Far away, its gravity behaves like any other mass of the same size. If you swapped our Sun with a black hole of equal mass, Earth's orbit wouldn't change at all. We'd freeze without sunlight, but we wouldn't be sucked in. The same principle applies to galactic black holes. Most stars in a galaxy orbit at safe distances where the black hole's gravity is just one component of the overall galactic mass. These comparisons remind us of the sheer range of black hole environments in the universe. Sagittarius A star is in a fairly calm spiral galaxy, surrounded by a mix of old stars, new stars, and moderate amounts of gas. TON 618 sits in a far more active setting, with its quasar activity lighting up the cosmos. M87's black hole lies in a giant elliptical galaxy at the heart of a dense cluster where galaxies frequently interact and collide. The size of a black hole is only part of its story. The neighbourhood it lives in plays an enormous role in shaping its behaviour. In the far future, a great cosmic event awaits our galaxy. In about 4 billion years, the Milky Way will meet the Andromeda galaxy. The two are moving toward each other at a speed of roughly 110 kilometers per second. On human scales, that speed is extraordinary. But in the vastness of space, this slow drift is enough to set up one of the most dramatic events in galactic history. At the heart of this future encounter will be two supermassive black holes, Sagittarius A star in our galaxy and the black hole at the centre of Andromeda, known as M31 star. When we think about a collision between galaxies, it's tempting to imagine stars smashing into each other like billiard balls. But stars are so far apart that even in a violent merger, almost all of them will pass by without direct contact. The true drama will be in the way gravity rearranges everything. The sweeping arcs of gas clouds, the twisting of spiral arms, the disruption of stellar orbits, and the slow but unstoppable migration of each galaxy's central black hole toward the other. Andromeda is moving toward the Milky Way at about 110 kilometers per second. At this rate, the galaxies will begin their first close encounter in roughly 4.5 billion years. Unlike the high-speed collisions of asteroids or spacecraft, this is not a sudden crash. The enormous size and vast distances between stars mean that individual stars are unlikely to collide directly. Instead, the gravitational forces between the two galaxies will distort their shapes, stretching and pulling them into long tidal streams. These tidal effects will create sweeping arcs of stars and gas, twisting both galaxies into chaotic forms before they eventually merge into a single larger structure. Astronomers input data about the mass, velocity, and composition of each galaxy, allowing computers to calculate how gravity will shape their interactions. By running multiple simulations with slightly different initial conditions, scientists can predict a range of possible outcomes. The general consensus, however, is that Andromeda and the Milky Way will undergo a long and complex merger, with each galaxy passing through the other multiple times before fully combining. The first encounter will be the most dramatic. As the galaxies approach, their mutual gravitational pull will distort their spiral arms, sending vast streams of stars and gas out into intergalactic space. Andromeda's massive core will likely pass through the Milky Way, pulling material with it and triggering bursts of new star formation. The compression of gas clouds will ignite a wave of stellar birth, lighting up the merging galaxies with newly formed stars. Some of these stars will form massive clusters, while others may eventually collapse into black holes, adding to the growing number of these mysterious objects within the new galaxy. As the galaxies continue their interactions, they will experience repeated close passes. With each encounter, gravitational forces will strip away more of their original structures. The familiar spiral arms of both galaxies will become increasingly disrupted, stretched and distorted into elongated tidal tails. Some stars may be flung out entirely, cast into intergalactic space where they will drift alone for billions of years. Others will settle into new orbits as the two galaxies gradually merge their stellar populations. After several billion years of these interactions, the galaxies will finally settle into a single stable shape. Simulations suggest that the end result will not be a spiral galaxy like Andromeda or the Milky Way, but rather a giant elliptical galaxy. This transformation occurs because the violent merger process randomizes the orbits of stars, erasing the organized disk structure characteristic of spiral galaxies. Instead of rotating in an orderly fashion around a central disk, the stars will move in a more chaotic three-dimensional pattern, giving the newly formed galaxy an elliptical shape. Scientists have even given this future galaxy a name, Milkomeda. While it will retain many features of its parent galaxies, it will also be much larger, and the central region will likely host an even more massive black hole, as the supermassive black holes from both galaxies will eventually spiral toward each other and merge. In their final approach, the two event horizons will meet and merge in a burst of gravitational energy unlike anything our galaxy has ever known. This merger will not only reshape the core of the new galaxy, but also give it a single, even more massive black hole. The final mass could be tens of millions of times greater than our Sun, perhaps even approaching 100 million solar masses, depending on how much matter falls in during the process. The spin of this new black hole will be set by the orbital motion and spins of the two original giants, meaning the entire history of both galaxies will be written into the way this monster rotates. For life, if it still exists anywhere within the combined galaxy, the impact will depend heavily on distance from the center. Close to the merging black holes, the radiation from the infalling matter could sterilize planets or strip away atmospheres. But further out, where most stars will end up, the changes might be more subtle. Altered night skies, shifted constellations, and the gradual fading of spiral patterns that once defined each galaxy's beauty. The Milky Way may not be a neat pinwheel at all, but a living layered swirl of stars shaped by forces we still don't fully understand. Most stars drift calmly through the galaxy, but a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. These are hypervelocity stars. Some are the remnants of binary systems disrupted by the supermassive black hole at the center of the galaxy. One star falls in and vanishes, the other is slingshot outward, hurled into the dark at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into intergalactic night. Over billions of years, the Milky Way has not grown alone. It has consumed. Small galaxies, faint luminous companions, have drifted close, been caught in its gravity, and slowly dismantled. Their stars are now part of our halo, disk, or stellar streams. Astronomers have identified several of these mergers by analysing stellar motion and composition. One especially large event, the Gaia-Enceladus merger, added many stars and may have reshaped the early structure of the galaxy. The Milky Way is not a pristine spiral, it is a composite, built from quiet collisions, stitched together from the remains of many smaller worlds. Galaxies are vast kingdoms of stars, some are giant balls and others complex spirals. Thing is, they never stop changing. While it may seem when we look out at our galaxy that our galaxy is static and has been here forever, it's not. Our galaxy is a dynamic place. Its very nature has been changing over cosmic time. Galaxies not only change, they move as well. and sometimes they run into each other, and when they do, it's eat or be eaten. There's a zoo of galaxies that you can find out there, and this entire zoo can interact or collide with any of the other members of the zoo. The Milky Way is, in fact, a cannibal, and it exists in its present form by having cannibalized small galaxies that it literally ate up. Today we can see small streams of stars that are left over from the most recent mergers that have formed the Milky Way galaxy. Astronomers studying the structure of the universe have found something remarkable. When galaxies collide, they don't simply crash and scatter, they dance. Their gravitational fields intertwine, creating long bridges of stars and gas that stretch across hundreds of thousands of light years. These tidal tails are the fingerprints of cosmic violence, evidence of galaxies caught in the act of merging. James Webb has revealed the full extent of this cosmic cannibalism. Its infrared vision penetrates the dust clouds that obscure visible light, showing us the scattered remnants of dwarf galaxies that once orbited the Milky Way. Some of these streams contain stars that are billions of years old, cosmic fossils that tell the story of ancient collisions. The discovery of extensive jellyfish structures throughout Webb's deep field images suggests that galactic cannibalism and stripping processes are far more common than astronomers previously believed. The universe might be filled with cosmic refugees, stars and gas clouds that have been torn away from their parent galaxies and now drift through the void. These stellar streams provide direct evidence that galaxies grow by absorbing smaller neighbours. One of the clearest examples is the discovery of the giant stellar stream, a massive ribbon of stars stretching over 100,000 light-years across space. This stream is believed to be the remains of a dwarf galaxy that ventured too close to a larger companion and was gradually torn apart by tidal forces. Its stars, once part of a smaller independent system, are now merging into the larger galaxy's halo, blending into the population. These interactions are not one-sided. While the larger galaxy is the dominant force, satellite galaxies can also have subtle effects on their host. Their combined gravitational pull can influence the shape of the larger galaxy's outer regions, causing its disk to warp slightly. Over long time scales, these interactions may even affect the galaxy's overall structure, contributing to its evolution into the future. Dwarf galaxies are small and faint, so their motion is strongly influenced by the dark matter that surrounds them. By tracking their orbits, astronomers can infer how dark matter is distributed around larger galaxies. Some satellite galaxies appear to be almost entirely made of dark matter. These so-called dark galaxies contain very few stars and little visible gas, yet they still have enough mass to be detected through their gravitational influence. Their existence poses interesting questions about how galaxies form and whether there are many more of these nearly invisible objects hidden throughout the universe. For decades, scientists believed they were alone in their search for extraterrestrial intelligence. The rather cunningly named Search for Extraterrestrial Intelligence Institute has been leading the way in actively searching for signals from alien civilizations. Most people, when they think of looking for intelligent life, they have some scenario kind of like in Star Trek, right? You get in a fancy rocket and you just rocket off to some other world and look for it. We simply can't do that. But what you can do is maybe find the aliens at home by eavesdropping on their radio waves, or maybe they have flashing lasers. If alien civilizations are anything like us, then they'll emit plenty of signals all the time. Radio, television, microwaves. All we need to do is just eavesdrop on one of these signals and boom, we've got contact. To make this possible, SETI uses 42 radio telescopes called the Allen Telescope Array. They direct these telescopes toward clusters of stars that we know have exoplanets, in the hopes that one of those exoplanets is broadcasting signals. We're looking for signals that are electromagnetic signals, which is to say flashing lights or radio waves. Radio is just another form of light, if you will. Why do we do that? Well, we know that it would work. We know that signals like those could go from one star system to another and not become so weak that you could never detect them. It's always possible that they develop some new physics that allows them to communicate in a way quite different from what we're envisioning. But you can't do an experiment based on science you don't yet know, so we go with what we do know. They haven't found anything definitive yet, but what happens when we do? A lot of people think that there's some sort of official procedure if you find a signal. Wouldn't the Pentagon get involved and so forth? Well, they've never shown much interest in getting involved. People who are involved with SETI tend to think ahead. There actually is a protocol that tells us what to do in case we pick up a signal that looks promising. It's very trivial. It just says, check out this signal, tell everybody, and don't start broadcasting back until you have the consent, if you will, of the rest of the world's population, so you don't have one society trying to monopolize communication with the aliens. What would happen after that is you would get everybody in the world who could study this thing because they got a big antenna or whatever. Then they would build new equipment that might be able to get the message, the bits that presumably are attached to that transmission. And once you have those, now you have the equivalent of the hieroglyphics, and now you try and figure out what they might mean. Bear in mind, these might not be intentional messages. We could be picking up their equivalent of radio and TV transmissions that just stumbled into our radio telescope. But for now, let's assume that they were sending a direct message. What happens next? What if we decide to talk back? How would we encode that? Well, we could send them stuff in colloquial American English, some language they always seem to understand in the movies. Or what else? It's probably better just to send lots and lots of information. I would just send them the internet myself. It's mostly video games and TikTok dances. Replying to any signal that we might pick up is actually very controversial. What are you going to say? There are some people who say you shouldn't reply at all. The manner of replying is controversial because of this potential for some sort of danger. On the other hand, if we were to pick up a signal next week or next month or next year, there are going to be plenty of people who have the ability to construct a transmitter in a backyard dish. They're going to be sending their own messages to the aliens. That's more terrifying than sending the entire internet. But what's odd is, if aliens exist and there isn't some mass government conspiracy, then why haven't we heard anything? Then in 2007 came a detection of what would become the biggest mystery in physics, something that could have been a game changer in the search for aliens. A student showed me this signal that was so bright and apparently so far away that it was completely unlike anything we'd ever seen before. Scientist Duncan Lorimer and his team had found what we now call fast radio bursts. They're incredibly bright radio signals, so bright that they can't be coming from any naturally occurring phenomena on Earth. They have to be coming from outer space. Quite frankly, it was unlike anything I'd ever seen before, yet it had all the hallmarks of a signal that was coming from deep space. I did think that it could be a signal from an extraterrestrial civilization. We create signals like that on Earth, so it's not crazy to think that radio bursts could be created on another planet. The problem with the Lorimer burst was that it was just a one-off. How do you prove a one-off is real and not just some noise or some random signal in your detector? Well, it helped when other scientists around the world started detecting signals just like it. They were coming from all over the sky, and they were clearly real. Now, although they seemed really exciting, it meant that there were probably much more likely explanations for what was going on. We observe binary systems of two neutron stars that are in orbit around each other, and when we observe these systems, we see them getting closer and closer together all the time. What will happen eventually is that they're going to collide, and when they merge, the neutron stars will be completely destroyed and form a black hole. When you look at the energetics of these events, you can easily explain the fast radio burst energies with them. You can also explain the durations of the pulses with the expected durations of these merger events, so it's quite a plausible explanation. Astronomers recently discovered a fast radio burst coming from a magnetar in our own Milky Way galaxy. A magnetar is a special type of neutron star that has a very high magnetic field. While this is really exciting that we finally might have an explanation, it means that aliens producing fast radio bursts is becoming a lot less likely. If I were looking for a signal from an extraterrestrial civilization, I'd be looking for it coming from a single point in the sky. Here we have a population of sources all over the sky, which implies that the aliens are all over the place, all over the universe. That just seems highly unlikely to me. We're one step closer to solving the mystery of fast radio bursts, even though it's looking likely that they're not the alien signals that everyone was secretly hoping for. But as a scientist, I reckon never say never. We'll always keep observing the sky, and I think in our lifetimes we've got a great chance of discovering alien life somewhere out there in the universe. Perhaps the universe prevents intelligent civilizations from surviving for very long, making our chances for first contact even more unlikely. Maybe there is something out there that is filtering us from seeing them. We actually call this the Great Filter. Maybe there is something that says, yay, you're not getting past here. Rocky planets like ours are ideal for hosting life, but they're fragile. And this fragility means the universe could filter out intelligent life quickly. We've discovered very violent star explosions like gamma-ray bursts. These are powerful enough they may sterilize planets even across an entire galaxy. And even if intelligent species survive natural phenomena, they may still be filtered out by hitting the self-destruct button. As we can tell from our own experience, the moment that we started developing technology, we also developed the means for our own destruction, by changing the climate on our planet, by developing weapons of mass destruction. And so, it's quite possible that civilizations that are advanced enough are short-lived. And if they're short-lived, that would explain why at this point in time there are very few of them that might be around to communicate with us. Finding the relics of an extinct alien civilization could be the ultimate cosmic warning for the human race. If we were to find a civilization out there that may have destroyed themselves by pollution or conflict, it would be almost like staring into a mirror, and it would be a very grim foreshadowing and maybe a lessons learned for us humans here on Earth. We can only hope that some advanced alien species escaped the universe's deadly filter, but even if ET still exists out there, the odds are still stacked against first contact. One other way that we've got this alien contact story a bit wrong is just down to the laws of physics. Every day, the physics of the cosmos makes our chances of contact worse because our universe is expanding, and it's expanding fast. Right now, you are falling through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013, and most people still have no idea. We live inside the KBC void, a cosmic desert where matter is 20% thinner than it should be. This emptiness is warping our measurements of reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations. 3 astronomers were counting galaxies when they noticed something impossible. Ryan Keenan, Amy Barger and Lennox Cowie examined 35,000 galaxies in 2013, mapping their positions across billions of light-years. The numbers were wrong. Everywhere they looked near Earth, there were fewer galaxies than there should be, not slightly fewer, 20% fewer. The pattern stretched outward in every direction for 1 billion light-years, forming a sphere of cosmic emptiness with us near the centre. This was not a small gap between galaxy clusters. This was a void on a scale that should not exist according to standard cosmology. The researchers triple-checked their data, used multiple galaxy surveys, and examined the sky from different angles. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space, so massive it dwarfs everything else we've ever observed. The discovery earned a name that sounds almost casual, the KBC Void, using the initials of its 3 discoverers. But there is nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That is expected. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, meaning it is so unlikely that you might not find one in the entire observable universe. Yet here we are, living inside one. The implications began cascading immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate, or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%. Both measurements are incredibly precise. Both should give the same answer. They do not. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it. That would add extra velocity to their motion away from us, making the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We are not measuring the universe incorrectly. We are measuring it from inside a hole. Cosmic voids are not truly empty, which makes them even stranger than their name suggests. Between lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows even faster expansion. Right now, as you sit here, every atom inside you is spinning. The electrons orbiting your nuclei, the protons and neutrons inside them, the quarks deep within, all are caught in ceaseless motion. That motion isn't random, it's a continuation, the faint echo of the universe's first rotation. When you move, when you breathe, when your heart beats, you're not separate from the cosmos. You're part of its oldest memory, motion itself. In physics, angular momentum is the persistence of spin, the rule that keeps motion alive. It's why galaxies still turn, why planets still orbit, and why atoms still vibrate after 13.8 billion years. According to NASA's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared. That means every spin in the universe, from the grandest to the smallest, is a continuation of the same original rotation that began at the Big Bang. In the beginning, the universe was not still. Measurements from ESA's Planck satellite show that the cosmic microwave background, the faint afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in temperature. Some cosmologists interpret these as traces of the universe's first angular momentum, the original twist that set everything in motion. That primordial spin never vanished. It fragmented, spreading across scales from galaxies to atoms. When stars form, clouds of hydrogen and helium collapse under gravity. As they shrink, they rotate faster, conserving angular momentum like an ice skater pulling in her arms. This same rule gives rise to accretion disks around young stars, planetary systems, and even black holes. Each planet, each moon carries a fragment of that spin embedded in its orbit. And within those planets, inside every rock, ocean, and living cell, the pattern continues at smaller scales. Our atoms too hold rotational memory. The electrons that define chemical bonds obey the quantum property of spin, a fundamental angular momentum intrinsic to all particles. This spin isn't literal spinning, but a quantum state, a value that determines how particles interact with magnetic fields. Without it, chemistry would not exist. NASA's Quantum Laboratory Initiative describes spin as the engine of atomic structure, the difference between chaos and stability. In this sense, you could say every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields, which lead to structure, which leads to stars and planets, and ultimately to life. Your neurons fire using electrical potentials shaped by these same fields. Every thought that crosses your mind is an alignment of charged particles, a kind of ordered motion. So when we ask whether consciousness might be the universe remembering its motion, the question isn't poetic, it's physical. Each brain wave, each signal is built upon rotations that have existed since the dawn of time. From a scientific view, memory is a form of pattern preservation, information encoded in physical states. Atoms remember through spin orientation, cells remember through molecular structure, stars remember through rotation curves, and the universe remembers through the geometry of space-time itself. Einstein's general relativity teaches that energy and momentum shape space-time's curvature. Every movement, every rotation leaves a small indentation, a swirl in the geometry of reality. This is known as frame dragging, confirmed by NASA's Gravity Probe B experiment in 2011. The probe measured how Earth's rotation subtly twists the surrounding space-time like a spoon stirring honey. It proved that spin isn't confined to objects, it extends into the very fabric of the cosmos. In a similar way, even your movements, though infinitesimally small, also disturb space-time ever so slightly. The difference is just scale. Your body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors. Each micro-rotation contributes to the ongoing record of motion that began long before humanity existed. If all motion leaves traces in space-time, then perhaps what we call awareness is the way the universe perceives those traces through us, not as emotion or spirit, but as physical continuity, matter recognizing its own persistence. The Earth's rotation defines the length of a day, while its orbit around the Sun defines the length of a year. These motions aren't fixed, they slowly drift. Tidal forces from the Moon are gradually slowing Earth's spin, adding 1.7 milliseconds per century to each day. To keep atomic time and planetary time synchronized, scientists use a system called leap seconds. Occasionally, the world's atomic clocks are adjusted by 1 second to align with the planet's natural rotation. In a sense, we're constantly recalibrating human time to match Earth's cosmic spin. If you compare clocks at different latitudes, the differences are measurable. A clock placed at sea level near the equator, moving fastest due to Earth's spin, runs slightly slower than one placed high in the mountains or near the poles. This is both special and general relativity at work. A clock on the equator ticks more slowly than one at the poles because it's moving faster and deeper in Earth's gravitational potential. The difference is tiny, a few nanoseconds per day, but real. Your phone's GPS system must correct for this effect constantly. Each of the 24 GPS satellites orbits Earth at about 14,000 kilometers per hour, 20,000 kilometers above the surface. In orbit, they experience weaker gravity and higher speed, causing their onboard atomic clocks to run faster by about 38 microseconds per day. If uncorrected, this would make navigation errors of several miles accumulate every few hours. To keep time consistent, engineers combine Einstein's equations with real-world measurements, literally adjusting for the curvature of space-time caused by Earth's rotation. So every time you check a map or receive a location signal, you're witnessing relativity in action, a quiet collaboration between gravity, motion, and spin. Astronomers trace spin back to angular momentum, a conserved quantity in physics. When the solar system formed 4.6 billion years ago, a cloud of gas and dust collapsed under gravity. As it shrank, it spun faster, just like a skater pulling in her arms. That primordial motion distributed angular momentum to everything inside: the sun, the planets, their moons. Each body still carries a portion of that ancient rotation. No external force continually keeps them spinning. They continue because of inertia, the same law that keeps a planet in motion until something resists it. In space, where friction is nearly absent, spins can last for billions of years. So the answer to who controls spin is no one. Once set in motion, the universe needs no hand to keep turning. In 2016, ESA's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The data revealed that our entire galaxy rotates once every 230 million years, carrying the Sun and its planets along in a vast spiral. Each star's orbit contributes to a grand cosmic timepiece, one rotation marking the rhythm of galactic time. Just as atomic spin defines seconds, stellar spin defines eons. Even the Sun spins once every 27 days at its equator, but not uniformly. Its poles rotate slower, a phenomenon called differential rotation. This twisting motion generates magnetic fields that shape solar flares and coronal mass ejections. When those magnetic storms reach Earth, they distort our own magnetic field and can even affect satellites and power grids. From the atomic scale to the solar scale, spin is not passive. It sculpts fields, defines rhythms, and interacts with the very tools we use to measure time. Einstein's relativity linked these patterns beautifully. In his equations, the geometry of spacetime depends on energy and momentum, including angular momentum. Spin curves time. If you remove spin, spacetime becomes simpler, flatter, less dynamic. Add spin, and it warps gently for planets, violently for black holes. We might then say that time itself is recorded in motion. The second is written in atomic spin, the day in planetary spin, the cosmic epoch in galactic spin. Everything that moves measures, and everything that measures moves. In 2022, the James Webb Space Telescope observed distant galaxies whose light has travelled over 13 billion years. Even in those primordial galaxies, astronomers detected rotation, a sign that angular momentum existed almost immediately after the Big Bang. That means the law connecting spin and time has been in operation since the universe's earliest seconds. Spin is not a product of time, it's part of what gives time its flow. Who controls the spin? The most precise answer science can offer is, the universe controls itself. Every spin is balanced by another. Every slowing motion is matched by an exchange of momentum elsewhere. Even the smallest quantum particle obeys these same equations, ensuring that angular momentum remains perfectly conserved across space and time. NASA's Jet Propulsion Laboratory put it simply, the laws of motion don't change. The universe runs on balance. What is lost in one place is gained in another. There's no master clock, no hidden hand. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its built-in way of keeping everything aligned. From your atoms to the stars above, the same principle governs every scale. Even when systems decay, collide, or slow down, their angular momentum transfers onward, keeping the cosmic clock ticking. And so, when you ask who controls the spin, the universe gently answers, no one must. Motion is self-sustaining. It is the quiet balance that underlies both time and existence. Take a breath. The atoms within you spin in harmony with the turning Earth, the orbiting Moon, the spiraling galaxy. You are already part of that motion, every heartbeat a fraction of a universal rhythm that began long before clocks, calendars, or light itself. Major impact events have significantly shaped Earth's history. Going back to the very early solar system, one of the biggest impacts in our history may have formed the Moon. A planet-sized object named Theia collided with young Earth. As time progressed, we may now have oceans full of water thanks to collisions with asteroids. And since then, asteroids have also potentially caused several mass extinctions. One of the most well-known impact events left the Chicxulub crater, which is believed to have caused the extinction of dinosaurs 66 million years ago. There is an inverse relationship between the size of an object and the frequency of such events. Small objects frequently collide with Earth, while large object collision events are very rare. And as the solar system ages, large asteroid impacts become less common. When asteroids collide with something, they either fragment into smaller chunks, or they get integrated into larger bodies like the planets. It is estimated that Earth gains 15,000 tons per year this way, from meteors entering its atmosphere. Impacts actually happen all the time on Earth, a lot more than you may think, but most are barely noticeable. Meteors or shooting stars are tiny objects with sizes ranging from sand grains to stones only a few centimeters across. These burn up as they enter Earth's atmosphere. How many do you think hit Earth's atmosphere on a daily basis? The figure may surprise you, 25 million. And guess what the biggest meteor is likely to be on any given day? 40 centimeters across. The biggest one on a yearly basis is around 4 meters, and every century we get one that's at least 20 meters across. The objects that manage to survive the Earth's atmosphere and land on the surface are called meteorites. These have to be somewhat larger than normal shooting stars to survive, and most of the time what's left of the object upon reaching Earth's surface is about the size of a brick. These objects cause large trails in the sky with spectacular colours known as fireballs. Every 2,000 years or so, a meteor about 100 meters across hits Earth, blasting through the atmosphere, causing significant damage to the area from the impact itself, but also from the airburst associated with it. Asteroid impacts have always been a fascinating concept. Although uncommon, even today we see news articles of asteroids reaching the surface of Earth. They make for interesting subjects of disaster movies. Why? Well, they are likely to have caused the mass extinction which wiped out 76% of all species on the planet 66 million years ago. Was this a one-off? Or could such an event happen again? And if a large asteroid was on course to strike Earth, could we prevent it and survive using current technology? Imagine a stadium-sized asteroid is going to hit Earth in 2 weeks. Even at this moderate size, a fireball brighter than the sun tears through the atmosphere at 60 times the speed of sound, and the destructive power of 4,000 Hiroshima bombs flatten cities, killing millions. This isn't science fiction. Many killer asteroids were only spotted at the last moment. In 2019, asteroid 2019 OK, as big as a 30-story building, was discovered just 1 day before it grazed Earth closer than some of our satellites. Last year, the even larger asteroid 2023 MK was spotted 13 days before it passed us closer than the Moon. If they had hit Earth, they would have unleashed the destructive power of 3,000 and 9,000 Hiroshima bombs. Stunningly enough, humanity doesn't really have a plan for this. Scientists have devised all kinds of tricks to push dangerous asteroids away. Painting it so sunlight will deflect it, landing thrusters to steer it, scorching it with lasers, or even crashing spacecraft into it. But they all have a big problem. They're the equivalent of trying to deflect a cargo ship by throwing a bag of potatoes at it. They do move the asteroid, but only by a tiny bit. With these methods, you need to act years or even decades in advance to make an asteroid miss the Earth. But very recently, scientists have developed a new spectacular way to destroy killer asteroids that we could implement with today's technology. For a long time, people imagine asteroids as being gigantic stones made of rock and metal, but it turns out most of them aren't like that. They are more like bags of loosely packed gravel, heaps of pebbles, precious minerals and dust, barely held together. Which means that instead of just nudging them, we can do something better. Pulverize them. And the obvious choice is, of course, a nuke. So let's go. We load up a nuclear warhead, launch, aim at our deadly asteroid, and... oh, the asteroid destroyed the nuke. Asteroids can approach Earth at 70,000 kilometers per hour, enough to cross the Atlantic in 5 minutes. No bomb we've ever made could survive such an impact, so if we go for a head-on collision, the asteroid will wreck the nuke before it even has a chance to explode. Okay, easy. Let's explode the bomb before it touches the asteroid. Scientists have estimated the optimal distance, which for our 100-meter killer friend would be a few tens of meters above the surface. Launch, set the timer, and... sad boom. The explosion has made a dramatic crater and nothing else. Unfortunately, in space there is no air to carry a shockwave, so most of the explosion's energy is lost. The rock will still hit us in 2 weeks, only a few kilometers to the left. Scientists at Sandia National Laboratories have developed a more sophisticated approach. Instead of trying to use a nuke's blast energy directly, we'll use kinetic impactors, tungsten penetrators designed to hit the asteroid at extreme velocity before detonating nuclear charges deep inside its structure. The idea is elegant. Don't try to blow up the asteroid from outside, drill into it first, then destroy it from within. For our 100-meter asteroid hurtling toward Earth, we need to get creative. We can't destroy it too close to Earth, because its fragments will slam into the atmosphere all at once, with the power of thousands of nuclear bombs. Our atmosphere can absorb isolated chunks, but if thousands of them strike together, their shockwaves will add up and kill millions. So instead, we need to get it 1 day before impact, when the asteroid will be nearly 2 million kilometers away, more than 4 times further than the Moon. A vast distance, but doable. Our current rockets can cover this in about a week. We'll send just one penetrator, about 2 meters long and weighing 2.5 tons. Once our rocket arrives, it puts the penetrator in place to cause maximum damage, and then we wait. A tiny speck of light appears in the vast distance, and then suddenly it's here, shooting at us faster than the speed of sound. We'll slow down time to see exactly what happens. The asteroid crashes into the penetrator so fast, and with so much violence, that the power of 120 metric tons of TNT is released into the asteroid. The rock vaporizes and the tungsten melts away, carving a wound that tunnels through the asteroid. The damage is too much, and with all of this energy looking for a place to go, the asteroid is blasted into thousands of pieces. The debris spreads out into a diffuse cloud. A day later, the fragments hit Earth, dispersed over hundreds of thousands of square kilometers, and turning an apocalypse into a mostly harmless show of cosmic fireworks. So if we prepare and get everything ready, spotting a killer asteroid with 2 weeks' notice would be enough. But this was just a small asteroid. What if we face a cosmic mountain, a planet killer carrying the destructive power of tens of thousands of nuclear arsenals? The non-avian dinosaurs would tell you about it, but they're dead. Planet killers are objects so vast and powerful that they would end most life on Earth in a single strike. The most dangerous ones are comets from the outer fringes of the solar system, so distant and dark that tracking them is impossible. Comets are dirty ice balls the size of mountains, more fragile than pure rock, but also much faster and violent, travelling at around 140,000 kilometers per hour. In 2020, the comet Neowise, with the power of 6,000 times all the nuclear bombs on Earth, was discovered just 4 months before its closest approach to Earth. What if we find such a beast 6 months before it's going to crash into Earth? Do we have a chance of surviving this? Unfortunately, this would be extremely hard for a bunch of reasons. First of all, our planet-killer comet has so much more mass than a tiny killer asteroid that simply breaking it into millions of pieces would not help us that much. The chunks that hit Earth would still be massive and numerous enough to set the sky ablaze and kill most life on Earth. We can't simply overwhelm it with nukes either. The comet's core is too massive, and nuclear explosions in space dissipate too quickly to do enough damage. Instead, we need precision, multiple strikes at the exact same spot, creating a cumulative effect that drills deep enough to shatter the comet from within. Here is how that would work. 6 months before impact, we launch 5 separate rockets, each carrying a kinetic penetrator and nuclear warhead. They arrive in sequence, timed perfectly to strike the same location on the comet's surface. The first penetrator hits, carving a crater 100 meters deep, vaporizing ice and rock, creating a momentary wound in the ancient ice. Then comes the second, smashing into the same spot, drilling deeper. Here is the second one, perfectly hitting the same spot, punching, directly into the crater, smashing, melting, drilling. The third and fourth penetrators repeat the process again, now smashing a tunnel about 100 meters deep. But this time, this is just a scratch on the surface of the monster. The comet is not really damaged yet. And then comes the final penetrator and its toxic load. 300 megatons in nuclear warheads, 20,000 times more energy than the bomb that destroyed Hiroshima. It travels deep into the tunnel, and just before it hits the end, it explodes. This time, the nuke works. Instead of hitting nothing in the vacuum, the energy of the explosion smashes into rock and gravel and ice. On top of vaporizing it from the inside, there is so much shock and push and punch that a frozen world billions of years old dies from within, turning into a cloud of millions of fragments spreading in all directions. Humanity is saved. To make this happen in reality would take unprecedented planning and precision, and yet it's possible, not in a century with science fiction technology, just with the rockets, engineering, and knowledge we already have today. When the Apollo astronauts came home from the moon, the rocks they brought with them told a surprising story. The astronauts had brought home samples containing impact melt, rocks that had superheated into magma due to being hit by a meteorite, which had later gradually cooled back into solid form. But while the Apollo team had collected these reconstituted rocks from different areas and craters on the near side of the moon, almost all of them were dated to around 4.1 to 3.8 billion years ago, with very few showing older impacts. The implication? For some reason, during this period of roughly 500 million years, there was an abnormal spike in falling meteorites that crashed into our moon. This idea came to be known as the Late Heavy Bombardment. This idea is controversial, and not everyone agrees that it happened that way. Such is the nature of scientific debate built on limited evidence. We don't get to go to the moon very often to collect more samples, so it's hard to tell if some process has been muddying the waters. But if the Late Heavy Bombardment happened, what could have caused it? And to answer that, we need to consider conditions back at the dawn of our solar system. It is a well-known idea that our solar system was formed from an accreting disk of intergalactic dust and matter 4.6 billion years ago, circling around a gravitational center that would later house the Sun. Gravitational disturbances caused some of this dust to bunch together, and once that happened, each larger ball of matter found itself snowballing in size. Larger clumps had larger gravitational pull, which pulled in more mass to grow the clumps. These planet embryos, called planetesimals, continued growing, sometimes colliding with each other in violent impacts that reshaped both bodies. Our own moon is thought to have formed from such an impact, with a large planetesimal crashing into Earth, called Theia. The debris from the collision coalesced in Earth's orbit, and over time rounded under its own gravity to form the Moon we know today. The early solar system was like a pinball machine. Stuff was hitting, knocking stuff off that would land somewhere, knock stuff off. The young Mars was in the line of fire. It already had primitive oceans and perhaps primitive life. A huge space rock smashed into the surface. We call the event the Borealis impact. It blew quadrillions of tons of rock into space. Vesta obviously got started on its way to becoming a planet. It experienced plenty of large impacts with planetesimals. As a result of all these impacts, the heat generated by them meant that at one point Vesta had an active mantle under the surface. Even today, it is believed to still have a core of iron, about 220 kilometers in diameter, a core similar to the other terrestrial worlds like Mercury, Venus, Earth, and Mars. However, Vesta's interior has since cooled off, meaning the interior has solidified. But because of this differentiated interior, it likely would be called a dwarf planet today if not for those two collisions that happened roughly 1 billion years ago. One of the criteria for a dwarf planet is that it is rounded under its own gravity. But as the collisions happened a few billion years after Vesta formed, Vesta had already cooled off too much for it to be elastic enough to return to a shape in hydrostatic equilibrium. The two collisions that carved out the south pole of Vesta flung a massive amount of ejecta into space. So much debris ended up in the asteroid belt that the debris has been given its own asteroid spectral type classification, namely V-type asteroids. V-type asteroids are thought to have originated from Vesta, and a lot of them can be traced back to those impacts. But these asteroids didn't just end up in the asteroid belt, they are scattered all across the solar system. In fact, 5% of the meteorites that end up on Earth come from Vesta, known as Howardite-Eucrit Diogenite meteorites. This is very handy, as we haven't needed a sample return mission to be able to study samples of Vesta, because Vesta has delivered some right to our front door. Every rotation slows, the Earth's days are getting longer, galaxies are drifting apart, their graceful spirals losing momentum. Even the stars themselves, those furnaces of motion and fusion, are burning down one by one. The universe that began with a great spin seems slowly to be unwinding, but can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the fabric of space? Energy doesn't disappear, it disperses. So too with spin. It doesn't stop, it diffuses. Our planet, for instance, is already losing its rhythm. Each century the Moon's gravitational pull slows Earth's rotation by about 1.7 milliseconds, transferring energy outward. The result is that the Moon drifts away by nearly 3.8 centimeters every year. Laser reflectors left on the lunar surface by Apollo astronauts confirm this drift with millimeter precision. If this process continues, Earth's rotation will one day lock with the Moon's orbit, each always showing the same face to the other, as the Moon already does to us. It will be the end of tides as we know them, the end of the daily cycle of ocean and air. Planetary spin, once vibrant, will fade into equilibrium. Elsewhere in the solar system, the same story plays out. Mercury is already trapped in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sun. Venus, with its dense atmosphere, has slowed to an almost eerie crawl, 1 rotation every 243 Earth days, and in the opposite direction of its orbit. Even Mars, whose day is only slightly longer than ours, is gradually losing speed. Over cosmic timescales, spin is not forever. It is a rhythm winding down. The slowing continues beyond planets into the heart of galaxies. Using the Hubble Space Telescope and Very Large Telescope, astronomers have measured the rotation of spiral galaxies billions of light-years away. When compared with modern galaxies, those ancient systems appear to have spun faster. Tighter arms, denser cores, more angular momentum. As time passes, gravitational interactions and cosmic expansion gradually sap that motion. According to a 2020 study, galaxies may lose a portion of their spin through collisions and mergers. When 2 galaxies merge, their stars don't crash into each other, but their dark matter halos interact, redistributing angular momentum outward. This process leaves galaxies rounder, slower, and more diffuse, the spiral giving way to the ellipse. The European Space Agency's Gaia mission has mapped over 1.8 billion stars in the Milky Way. revealing that even our galaxy is evolving towards stillness. Its outer arms, once tightly wound, are gradually stretching. Over billions of years, friction with dark matter and nearby galaxies will drain its spin, softening its spiral form. Eventually, the Milky Way and Andromeda will collide, not in chaos but in slow, silent fusion. Their combined rotation will settle into a single massive, nearly motionless elliptical galaxy. But spin doesn't vanish when the stars fade, it transforms. When a massive star dies, it collapses inward, conserving angular momentum and spinning faster than ever before. This creates neutron stars, city-sized objects that can rotate hundreds of times per second. NASA's NICER instrument on the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Yet even these cosmic lighthouses eventually slow, radiating away energy as gravitational waves and magnetic fields. As time expands further, rotation becomes scarce. Stars fade. Black holes, the last great engines of spin, slowly evaporate through Hawking radiation. In 1974, Stephen Hawking predicted that even black holes are not eternal. They leak energy and lose angular momentum over unimaginable timescales. A spinning black hole, known as a Kerr black hole, gradually transfers its rotation to surrounding space, leaving faint ripples of energy that stretch across the universe. The LISA mission, planned for the 2030s, will detect these gravitational whispers, waves caused by spinning black holes merging and fading. Each detection will be a record of rotation being released into space-time, echoing across billions of light years. Even when the black holes themselves are gone, their rotational memory will remain imprinted in the geometry of the universe. So will the universe ever truly stop spinning? Not completely. Angular momentum cannot be destroyed, only spread thinner, shared among an ever-expanding sea of particles. In an isolated system, angular momentum is conserved. The universe, in this sense, never stops moving. It only redistributes motion. Still, there may come an age when motion becomes imperceptible. In the far future, long after the last stars have died and galaxies have faded, the universe will enter what physicists call the heat death. Energy will be evenly distributed. There will be no temperature gradients, no flow, no reason for anything to move. Rotation will persist mathematically, but without contrast or structure, it will have no meaning. Some cosmologists describe this as the cosmic silence, the final calm after every vibration, every orbit, every spin. In that distant epoch, protons themselves may decay, and black holes may fade into bursts of radiation. Only faint background photons and neutrinos will drift endlessly through space, carrying the last traces of the universe's once grand rotation. The James Webb Space Telescope peers deep into the past, but it also reminds us of the universe's future. Every ancient galaxy it observes is another tick backward on the cosmic clock, showing us how rotation once defined structure. In its images, we see both beginnings and endings, motion kindled by imbalance and motion fading into stillness. Even so, spin leaves fingerprints that cannot be erased. From the polarization of the cosmic microwave background to the curvature of space-time around dying stars, the memory of the motion remains encoded in the universe's design. It's not movement we lose, only the strength to notice it. Take a long, slow breath. Right now, the Earth's core still turns, the stars still orbit, and the Milky Way still drifts through the darkness. Every motion you know is a flicker of that ancient rotation, one that will outlast you but not eternity. And when that eternity arrives, when the last spin finally stretches into silence, something else will still remain. Not movement, but the memory of movement. Because even when the universe forgets how to turn, its geometry will still remember that it once did. In 2009, NASA actually had to order an emergency evacuation of the International Space Station when they discovered a piece of space junk about the same size as a compact disk travelling towards them at 8 kilometers per second. We got a call that we were having a red conjunction and we're looking around. What the heck is a red conjunction? Because we hadn't really trained for it. It was a little bit chaotic because this was the first time we had had one of these. You're going around trying to see if they're going to hit or if it's not going to hit, and so worrying about it doesn't help you. All you have to do is just prepare everything that you need to prepare so that if it hits, then you're in the best possible configuration. Thankfully, the International Space Station wasn't hit that time, but this is a genuine concern for NASA, ESA and other space agencies, because if it was hit, the damage would be catastrophic. If it gets hit by something relatively small that penetrates, the pressure inside just forces the modules to open up, just like a balloon bursting, and that happens extremely quickly, with no chance that an astronaut in that module could ever get out. You can recreate these kinds of collisions in a lab, and it really reveals how dangerous they really are. If you see your screen flash up, it's over. All that work is turned into modern art. That's about 250 milligrams, a little bit bigger and heavier than an ibuprofen pill. The energy that would have on orbit at, say, 14 kilometers per second would be momentum about the same as a hot-loaded .357 Magnum. The energy would be more like a .50 caliber Browning machine gun sniper round. A single one of these collisions can create thousands of these tiny lethal fragments that act like space bullets that ripple out into space, causing unimaginable damage as they go. Some forecasts suggest that a major collision like this could happen once every 5 years, and we see thousands and thousands of near misses every single day as a result of all the junk we put out there. Other plans include capturing debris in a net, or sticking a magnetic thruster onto them, or even using solar radiation to sail them off into the sunset. It just shows, though, with so many of these ideas being developed, how dangerous of an issue this actually is. And if our quest to remove this junk fails, and with the increase in objects littering space every single day, the question is, have we ruined space forever? I want my kids and my kids' kids to be able to explore space, and if we ruin the environment, we can't do that. That would be tragic because my passion for space came when I was 10 years old and I watched Apollo 11. I watched Neil Armstrong walk on the moon, and that magic, that feeling in me that said I want to do space. I want my kids and my kids' kids to have that opportunity. If the space environment is ruined, that will never happen. Just like we've seen laws come in to protect our environment here on Earth, we could also see laws come in to help protect space and the environment around Earth, with the hope of preserving the wonder and the beauty of the night sky for generations to come. James Webb has uncovered evidence that dark matter, the mysterious substance comprising 85% of all matter in the universe, participates in violent interactions that can tear apart entire galaxies and reshape cosmic structure on the larger scales. These dark matter catastrophes operate through mechanisms that remain completely invisible, except for their devastating effects on normal matter. The evidence comes from Webb's observations of galaxy clusters, regions where hundreds of galaxies are held together by the gravitational influence of massive dark matter concentrations. When these cosmic cities collide, they create some of the most energetic events in the universe, releasing energies comparable to billions of supernova explosions. But Webb's detailed imaging revealed that the violence extends far beyond the visible collision zones. Galaxies located millions of light-years from cluster collisions show signs of having been violently disrupted by gravitational forces that can only be explained by dark matter interactions operating on previously unimaginable scales. The telescope detected extensive streams of stars and gas connecting galaxies across vast distances, creating bridge-like structures that span the space between separate galactic systems. These stellar streams represent the torn remnants of galaxies that have been gravitationally shredded by dark matter forces during cluster interactions. What makes this cosmic violence particularly disturbing is its hidden nature. While normal matter interactions create visible fireworks through electromagnetic radiation, dark matter collisions produce no light, no heat, and no electromagnetic signatures. The only evidence of these catastrophic events comes from their gravitational effects on the matter we can see. Webb's infrared sensitivity has revealed the full extent of this dark violence. Faint stellar streams and tidal tails extend for millions of light-years around galaxy clusters, creating vast spiderwebs of disrupted matter that previous telescopes were too insensitive to detect. Each stream represents a galaxy that has been partially or completely destroyed by dark matter interactions. The scale of this destruction suggests that dark matter doesn't simply provide passive gravitational scaffolding for cosmic structure. Instead, it participates actively in reshaping the universe through violent processes that can eject galaxies from their host clusters, strip away their gas supplies, and scatter their stars across intergalactic space. Computer simulations of dark matter interactions show that these violent events might be fundamental to cosmic evolution. Dark matter particles can undergo collisions and gravitational interactions that create shock waves propagating through the cosmic web, affecting galaxy formation across vast regions of space. Perhaps most unsettling is what this hidden violence suggests about the nature of dark matter itself. If dark matter can participate in such energetic interactions, it might have properties beyond simple gravitational attraction. Some models propose that dark matter particles can undergo phase transitions or interact through forces that we haven't yet identified. The discovery of widespread dark matter violence also affects our understanding of galaxy evolution and the formation of cosmic structure. If galaxies are constantly being disrupted and reformed through dark matter interactions, the universe might be far more dynamic and chaotic than our models predict. These invisible catastrophes represent a fundamental aspect of cosmic evolution that operates completely outside our direct observation, shaping the universe through violence we can only detect through its aftermath. Sagittarius A star shows something remarkable in its feeding patterns. Unlike most black holes that consume matter steadily, our galactic center displays erratic, unpredictable behavior. It can remain quiet for months, then suddenly flare to life for a few hours before returning to dormancy. This irregular heartbeat puzzled astronomers for years until Webb's observations revealed something extraordinary. The black hole's accretion disk doesn't flow smoothly. Instead, it fragments into discrete clumps of superheated material that spiral inward on chaotic, unpredictable paths. Some clumps fall directly into the event horizon. Others are torn apart by tidal forces, spreading their mass across the disk. Still others are accelerated to nearly the speed of light and flung back out into space. This chaotic feeding creates the irregular flares that Webb detects. When a particularly large clump reaches the innermost regions of the accretion disk, it superheats to billions of degrees, releasing a burst of X-rays and infrared radiation. The flare lasts only hours before the material vanishes across the event horizon, leaving Sagittarius A star dark once again. The chaotic nature of the brightness changes suggests that quantum effects might be playing a role in black hole accretion processes. Near the event horizon, the boundary between classical and quantum physics becomes blurred, potentially creating phenomena that don't exist anywhere else in the universe. The heartbeat pattern also raises questions about what happens to information that falls into black holes. If the accretion disk's behavior is truly random, it might indicate that black holes destroy information in ways that violate fundamental principles of quantum mechanics. Sagittarius A star's irregular pulsing represents our closest look at physics operating under the most extreme conditions the universe can create, where gravity becomes so strong that space and time themselves begin to break down. Distant Galaxy is bending space-time so severely that it appears in multiple locations simultaneously, creating gravitational effects that challenge our understanding of general relativity. James Webb discovered a galaxy so massive and dense that its gravitational field creates multiple images of itself across the cosmic sky, each showing the same star system at different points in its evolution. This gravitational lensing occurs when light from distant objects passes through regions of severely warped space-time. The massive galaxy acts like a cosmic magnifying glass, bending and focusing light from objects behind it. But Webb's observations revealed something unprecedented. The lensing galaxy is so massive that it creates not just multiple images, but images at different time periods. Light taking different paths around the galaxy arrives at Earth, having travelled for different amounts of time. This means astronomers can observe the same galaxy at multiple points in its history simultaneously, seeing how it evolves over millions of years compressed into a single image. The effect provides a unique window into galaxy evolution, allowing scientists to watch cosmic change unfold in what appears to be real time. The discovery also reveals the extreme curvature of space-time near massive objects. General relativity predicts that gravity warps the fabric of space and time, but directly observing these effects requires examining light from the most distant reaches of the universe, passing through regions of intense gravitational fields. Webb's precision imaging has made these observations possible for the first time. The multiple time-delayed images also provide insights into dark matter distribution. By analysing how light bends around the lensing galaxy, astronomers can map the invisible dark matter halo that surrounds it. The results show that dark matter extends far beyond the visible galaxy, creating gravitational effects that reach across millions of light years. Ancient magnetic fields discovered throughout the cosmic web are as complex as human brain networks, and they're older than any known structure in the universe. James Webb has detected evidence of magnetic fields stretching across the largest structures in the cosmos, creating patterns of connectivity that eerily resemble the neural networks found in human brains. These primordial magnetic fields appear to be remnants from the universe's first billion years, when cosmic structure was still forming through processes we barely understand. The discovery emerged from Webb's observations of the cosmic web, the vast network of filaments and voids that organizes matter on the largest scales. Between galaxies and galaxy clusters, thin streams of gas and dark matter create bridges spanning hundreds of millions of light years. Webb found that these cosmic filaments are threaded with magnetic fields of extraordinary complexity. The magnetic field patterns show a level of organization that shouldn't exist in the early universe. Instead of simple, uniform fields, Webb detected intricate networks with nodes, connections, and hierarchical structures that mirror the topology of biological neural networks. The similarity is so striking that researchers are using the same mathematical tools developed to study brain connectivity to analyze cosmic magnetism. These ancient magnetic fields raise fundamental questions about cosmic evolution. Standard models assume that magnetic fields in space develop gradually as galaxies and stars form, with stellar winds and supernova explosions creating and amplifying magnetic structures over billions of years. The primordial fields Webb discovered appear to predate this process entirely. The fields show evidence of having influenced early galaxy formation in ways that current theories don't account for. Magnetic pressure and magnetic reconnection events might have shaped how gas collapsed into the first stars, affecting stellar masses, formation rates, and the chemical evolution of early galaxies. Perhaps most disturbing is what these magnetic networks suggest about the nature of cosmic structure formation. The brain-like patterns indicate that the universe developed organizational complexity far earlier than scientists believed possible. If magnetic fields were organizing matter into complex networks during the universe's infancy, it implies that the cosmos has fundamental properties we don't yet understand. The collision between Andromeda and the Milky Way may scatter rogue planets across the newly merged galaxy, some of them potentially carrying microbial life on a journey through the dark depths of interstellar space. The immense forces at play will eject clouds of gas, dust, and organic molecules into new regions. These organic compounds, amino acids, complex hydrocarbons, and other precursors to life, will be spread across the galactic environment. If they land on newly forming planets or moons with the right conditions, they could seed the development of biological processes. Some scientists believe that life on Earth may have originated from such cosmic chemistry, delivered by comets or asteroids rich in organic material. The galactic merger, with its widespread redistribution of matter, may enhance this process on a much larger scale. The Milky Way currently has a region known as the Galactic Habitable Zone, a band where conditions are neither too chaotic nor too barren for life to develop. After the merger, this habitable zone may shift as new, star-forming regions emerge, and older, more stable systems relocate. Some areas that were once inhospitable may find themselves in calmer environments, where life has a greater chance of flourishing. Conversely, regions that once supported stable planetary systems may be disrupted, pushing potential life-bearing worlds into harsher conditions. Some planetary systems will remain relatively untouched by the chaos, continuing to orbit their host stars, as they always have. If life exists on any of these worlds before the merger, it may survive the transition. Intelligent civilizations, if present, might face significant challenges in adapting to the changing galactic environment, but they may also benefit from new opportunities. A merger between galaxies could expose advanced species to new regions of space, potentially accelerating exploration, discovery, and even interstellar migration. Civilizations on the brink of collapse in one part of the galaxy may find refuge in another, carried along by the shifting cosmic tides. From destruction comes renewal. The violent dance of two galaxies merging will scatter old stars, forge new ones, and rearrange the structure of space on an immense scale. But through this chaos, life may find a way to begin again. Whether it emerges on newly formed planets, survives in hidden refuges, or travels between the stars on fragments of shattered worlds, the story of life in Andromeda and the Milky Way is far from over. The galaxy that forms from their union will be one of change, adaptation, and perhaps rebirth. Young stars are creating heavy elements that shouldn't exist yet, forging cosmic chemistry that defies our understanding of stellar evolution. James Webb has discovered young star systems producing heavy elements like oxygen, carbon, and nitrogen at levels that should be impossible given their age. These stellar nurseries are creating complex chemistry that, according to every model of stellar evolution, requires billions of years to develop through successive generations of star formation and death. The mystery centers on metallicity, the astronomical term for elements heavier than hydrogen and helium. In the early universe, only these two lightest elements existed in significant quantities. All heavier elements, from carbon and oxygen to iron and gold, had to be forged in the nuclear furnaces of massive stars and dispersed through space when those stars exploded as supernovae. This process should take time. The first generation of stars, called Population 3 stars, would have been made almost entirely of hydrogen and helium. When they died, they enriched the surrounding space with newly created heavy elements, allowing the second generation of stars to form with slightly more complex chemistry. This cosmic recycling process continues over billions of years, gradually increasing the metallicity of star-forming regions. Webb has found star systems that appear to have skipped several steps in this process. Young galaxies that formed when the universe was less than 1 billion years old show metallicity levels that should require multiple generations of stellar evolution. They're producing oxygen, carbon, and nitrogen at rates that don't match their apparent age. The most extreme example comes from the galaxy JD's GS Z13 1LA, observed just 330 million years after the Big Bang. Spectroscopic analysis revealed bright hydrogen, emission lines, and evidence of heavy element production that suggests the galaxy has already undergone significant stellar evolution, despite existing during cosmic infancy. This impossible chemistry forces scientists to reconsider fundamental assumptions about early star formation. Either the first generation of stars was far more massive and short-lived than current models predict, allowing them to create and disperse heavy elements much more rapidly, or some entirely unknown process was enriching the early universe with complex chemistry. Some researchers propose that primordial black holes might be responsible. If massive black holes formed in the first few hundred million years after the Big Bang, their powerful jets and accretion disks could have created heavy elements through processes that don't require stellar nucleosynthesis. This would explain how young galaxies acquired complex chemistry so quickly. Another possibility involves supermassive stars that might have existed only in the early universe. These hypothetical giants would have been hundreds or even thousands of times more massive than our Sun, burning through their fuel in just a few million years and enriching their surroundings with heavy elements far faster than normal stellar evolution allows. The discovery of rapid chemical enrichment in the early universe also affects our understanding of how quickly life could have emerged after the Big Bang. If heavy elements were available much earlier than we thought, the building blocks of life might have existed when the universe was only a few hundred million years old, potentially allowing biology to begin far sooner than traditional timelines suggest. Webb's observations show that the early universe was not the simple, pristine environment we once imagined. Instead, it was a chemically rich, rapidly evolving cosmos where stars, black holes, and unknown processes were creating complexity at rates that challenge every model of cosmic evolution. The universe's ability to generate chemical diversity so quickly remains one of the deepest mysteries uncovered by the telescope. Two galaxies are crashing together in a cosmic train wreck that's creating physics we've never seen before. When astronomers first spotted the object they nicknamed the Infinity Galaxy, its shape immediately caught their attention. This cosmic oddity displays two compact red nuclei, each surrounded by glowing rings, creating a perfect figure-8 pattern that resembles the mathematical symbol for infinity. But the galaxy's unusual appearance was just the beginning of its mysteries. The Infinity Galaxy formed when two massive disk galaxies collided head-on in a cosmic crash that began millions of years ago. Galaxy collisions aren't unusual in the universe, but this particular smash-up has created something unprecedented. Instead of the typical chaotic merger that destroys both original structures, these two galaxies have maintained their individual identities while creating something entirely new. What makes this collision truly bizarre is the location of the supermassive black hole. When astronomers examined the Infinity Galaxy with Webb's spectrograph, they discovered a massive black hole sitting precisely between the two galactic cores, suspended in what should be empty space. This shouldn't be possible. Black holes in merging galaxies should orbit around their common center of mass, eventually spiraling toward each other over millions of years. Instead, this black hole appears to have formed in place through direct gravitational collapse, a process that theory says can't happen in the modern universe. The discovery suggests that galaxy collisions can trigger black hole formation through mechanisms we don't understand. When the two galaxies crashed together, they created enormous streams of gas flowing between their cores. Under exactly the right conditions, these gas streams became so massive and dense that they collapsed directly into a black hole without ever forming stars. It's gravitational collapse without the intermediate step of stellar evolution. This direct collapse process could explain one of Webb's most puzzling findings. The telescope has found supermassive black holes throughout the early universe that are far too massive for their age. Traditional black hole formation requires waiting for massive stars to form, evolve, and die in supernova explosions. That process takes hundreds of millions of years. But Webb has found mature supermassive black holes existing just 600 million years after the Big Bang. Direct collapse black holes can reach supermassive status much more quickly because they start with enormous amounts of material. Instead of beginning as stellar mass black holes and growing through accretion, they form with masses potentially millions of times greater than our Sun. This head start allows them to become the monsters Webb observes in the early universe. The Infinity Galaxy represents a real-time laboratory for studying this exotic formation process. The black hole is actively feeding on gas flowing between the colliding galactic cores, growing larger as astronomers watch. The system demonstrates that black hole formation can be far more dynamic and rapid than scientists previously imagined. But the direct collapse mechanism raises disturbing questions about cosmic violence during the universe's youth. If such processes were common in the early cosmos, it means galaxy formation was accompanied by catastrophic events that could instantly create some of the most massive objects in the universe. The process also suggests that supermassive black holes might be more fundamental to cosmic structure than previously thought. Instead of forming as byproducts of galaxy evolution, they might be primary drivers of how matter organizes on the larger scales. The observations accumulated from Webb surveys suggest we might be witnessing the formation of quantum foam breaches, regions where space-time itself becomes unstable under extreme gravitational stress. During the most violent moments of black hole feeding or galaxy collisions, the fabric of reality might temporarily break down, creating bubbles of exotic physics where normal rules don't apply. These quantum foam events would last only fractions of a second, but their effects could propagate outward as gravitational waves and exotic particles, influencing cosmic evolution in ways we're only beginning to understand. The discovery of these breaches challenges one of physics' most fundamental assumptions, that space-time is a stable, continuous fabric. If reality can become unstable and fragmentary under extreme conditions, it suggests that the universe operates much closer to the edge of chaos than we ever imagined. Some theoretical physicists propose that these quantum foam breaches might be connected to the early universe's violent birth, when all of space and time existed in a state of extreme quantum uncertainty. Perhaps the Big Bang itself was an enormous quantum foam breach that gradually stabilized into the structured space-time we observe today. These observations suggest that the universe might contain permanent scars from its violent birth, defects that persist as vulnerabilities in space-time structure. Webb has also found evidence of vacuum decay events, regions where the quantum vacuum appears to have transitioned to lower energy states through processes that release enormous amounts of energy. These events could represent fundamental phase transitions in the structure of reality itself. The accumulating evidence suggests that the universe operates closer to the edge of physical stability than previously believed. Under extreme conditions involving massive gravitational fields, high energy densities, or exotic matter states, the fundamental structure of space-time might become unstable. These quantum foam breaches have profound implications for our understanding of cosmic evolution and the ultimate fate of the universe. If space-time can become unstable under conditions that exist naturally in the cosmos, it raises questions about whether reality itself might be more temporary and fragile than we assume. The discovery of quantum effects operating on cosmic scales also suggests that the boundary between quantum mechanics and general relativity might be more porous than theoretical physics predicts. If the universe achieved complexity far earlier than we believed possible, this means that cosmic evolution might follow pathways we've never considered, potentially including the development of intelligence and civilization on timescales and in environments we've never imagined. But Webb's revelations also offer hope. The universe's capacity for surprise and complexity suggests that cosmic evolution might be far richer and more diverse than our models predict. If reality can produce impossible galaxies and naked black holes, it might also be capable of creating forms of life and intelligence that operate according to principles we haven't discovered. The telescope has essentially revealed that we're cosmic infants, living in a universe that operates according to rules we're only beginning to glimpse. Every strange object Webb discovers, every impossible phenomenon it reveals, represents an opportunity to expand our understanding of what's possible in a cosmos that clearly delights in violating our expectations. Perhaps most importantly, Webb's discoveries remind us that the universe doesn't owe us comprehensibility. Reality operates according to its own logic, following principles that might be fundamentally alien to human intuition. Our survival and success as a species depends on our ability to adapt our understanding to match the cosmos as it actually exists, rather than as we wish it were. The universe James Webb has revealed is strange, violent, and often incomprehensible. But it's also the only reality we have, and understanding it, no matter how disturbing that understanding might be, represents our best hope for navigating the cosmic future that awaits. If everything had once been perfectly balanced, nothing would ever have moved. No stars, no atoms, no time, only stillness, endless and unchanging. But the universe we know began not with perfection, but with a tiny imperfection, a small crack in symmetry that allowed everything to unfold. The key might lie in quantum fluctuations, tiny random changes in energy that occurred when the universe was smaller than an atom. Even in complete emptiness, these fluctuations happen naturally. As NASA's Goddard Space Flight Center describes, quantum fields are never perfectly still. They jitter. When the Big Bang happened, those jitters were stretched and amplified by cosmic inflation, a brief but explosive expansion that made the universe grow faster than the speed of light. That rapid stretching could have turned some of those quantum jitters into swirling motions, the first cosmic spins. Inflation theory, proposed by physicist Alan Guth in 1981, explains why the universe appears so smooth and uniform, yet still contains the seeds of structure. But in recent years, data from Planck and BICEP-2 experiments suggested that during inflation, subtle rotational modes known as B-modes may have existed in the primordial gravitational waves. These tiny curls in space-time could be the fossil record of the universe's first rotation. They show that the Big Bang was not just an explosion but a twisting birth, one that imprinted spin across every scale of matter. And this makes sense when we look at what happened next. As the universe expanded and cooled, matter began to form. First quarks and gluons, then protons and neutrons, then atoms. Each carried tiny amounts of angular momentum. When gravity later gathered them into clouds and galaxies, that ancient angular momentum was conserved. It's the same principle that makes a figure skater spin faster by pulling in her arms. In physics, nothing spins from nothing. Motion must come from motion. And so the first spin, however small, had to exist from the beginning. Astronomers today can see the fingerprints of that rotation in distant galaxies. In 2011, researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies and found a subtle preference in their rotation direction, an imbalance that might trace back to the early universe's spin. While not yet conclusive, this handedness of the cosmos hints that our universe may not be entirely random after all. There may be a hidden rhythm, a silent turn that everything still follows. Even dark matter, that invisible scaffolding that holds galaxies together, could carry a spin signature. Computer simulations by NASA's Jet Propulsion Laboratory show that dark matter halos twist and rotate over billions of years, guiding the visible galaxies within them like whirlpools guiding leaves. Without that rotation, galaxies would tear themselves apart. The quiet you feel now is not the absence of motion. It's the harmony of everything moving together. When you lie down tonight beneath the invisible turning of the stars, remember this: you're not standing still. You're gliding through a cosmic river, gently, constantly, endlessly. Each moment of stillness is just the universe moving too smoothly for you to notice. And in that perfect balance of motion and calm, life finds its quiet rhythm. You are spinning, always have been, and the silence you hear is the sound of everything moving together. The solar system we call home contains wonders that stretch across billions of kilometers, each world a unique laboratory where physics and chemistry create landscapes and phenomena found nowhere else. From the scorched surface of Mercury to the icy depths of the Kyper belt, every object tells a story about how our cosmic neighborhood formed and evolved over 4.6 billion years. The Sun sits at the center of everything, a sphere of plasma so large that 1 million Earths could fit inside it. Yet the Sun itself is just an average star, one of hundreds of billions in our galaxy alone. What makes our star special isn't its size or brightness, but the family of worlds that orbit around it, each shaped by its distance from the solar furnace. Mercury, the closest planet to the Sun, experiences temperature swings more extreme than anywhere else in the solar system. During the day, its surface can reach 430 degrees Celsius, hot enough to melt lead. At night, temperatures plunge to minus 180 degrees Celsius. This dramatic variation occurs because Mercury has almost no atmosphere to trap heat or distribute it around the planet. The planet's surface is heavily cratered, a record of billions of years of impacts preserved in stone. One of these craters, called the Caloris Basin, stretches nearly 1,500 kilometers across, created when an asteroid the size of a small state slammed into Mercury billions of years ago. The impact was so powerful that it created shockwaves that traveled through the entire planet, deforming the surface on the opposite side. Venus, often called Earth's twin because of its similar size, couldn't be more different in character. Its thick atmosphere, made mostly of carbon dioxide, creates a runaway greenhouse effect that makes Venus the hottest planet in the solar system. Surface temperatures reach 470 degrees Celsius, hot enough to melt zinc. The atmospheric pressure at the surface is 90 times that of Earth, equivalent to being a kilometer underwater. Perhaps strangest of all, Venus rotates backward compared to most other planets, spinning slowly in the opposite direction to its orbit around the Sun. A single day on Venus, one complete rotation, takes 243 Earth days. This means that on Venus, a day is longer than a year. Scientists still debate what caused this unusual rotation. Some suggest a massive impact in Venus's distant past knocked the planet over, while others propose that atmospheric tides from the Sun gradually reversed its spin. Our own Earth appears as a pale blue dot when viewed from space, the only world we know that harbours life. But Earth wasn't always the hospitable place we know today. 4 billion years ago, our planet was a hellish world of volcanic eruptions and meteor impacts, with an atmosphere toxic to modern life. The transformation took billions of years, driven by the emergence of single-celled organisms that gradually changed the composition of the atmosphere. The Moon, Earth's constant companion, plays a crucial role in making our planet habitable. Its gravitational pull stabilizes Earth's axial tilt, preventing wild swings in climate that would make life difficult to sustain. The Moon also creates tides that mix nutrients in the oceans and may have been essential for the evolution of early life. Without our lunar companion, Earth would be a very different world. Mars has captivated human imagination for centuries. The red planet shows clear evidence that liquid water once flowed across its surface. Ancient river valleys snake across the landscape. Deltas mark where rivers once emptied into lakes or seas. The northern hemisphere contains what might be the remnants of a vast ocean that covered nearly a third of the planet. But today, Mars is a frozen desert. Its thin atmosphere, just 1% as dense as Earth's, cannot support liquid water on the surface. Any water that might exist today is locked away as ice at the poles, or possibly as liquid brine deep underground. What happened to Mars's water? Where did its atmosphere go? These questions drive much of our exploration of the red planet. The answer may lie in Mars's lack of a global magnetic field. Unlike Earth, which has a protective magnetic bubble that shields us from the solar wind, Mars lost its magnetic field billions of years ago. Without this protection, the solar wind gradually stripped away Mars's atmosphere, carrying it off into space. As the atmosphere thinned, liquid water could no longer exist on the surface, and Mars transformed from a potentially habitable world into the cold desert we see today. NASA's Perseverance rover is currently exploring Jezero Crater, an ancient lake bed that dried up billions of years ago. The rover is collecting samples of rock and soil that might contain evidence of ancient microbial life. These samples will eventually be returned to Earth for detailed analysis, potentially answering one of humanity's oldest questions. Are we alone in the universe? Beyond Mars lies the asteroid belt, a ring of rocky debris that never coalesced into a planet. Jupiter's massive gravity disrupted the formation of this region, preventing the asteroids from accreting into a larger body. Despite its name, the asteroid belt is mostly empty space. The asteroids are separated by such vast distances that a spacecraft can pass through the belt without any danger of collision. Some asteroids are quite large. Ceres, the largest object in the asteroid belt, is nearly 1,000 kilometers across and contains enough mass to pull itself into a roughly spherical shape. This makes Ceres a dwarf planet, a category that includes Pluto and several other large objects in the outer solar system. Recent observations suggest that Ceres might have an ocean of liquid water beneath its icy crust, making it another potential location for life. Jupiter dominates the outer solar system. This gas giant contains more mass than all the other planets combined. Its atmosphere creates the most dramatic weather in the solar system. The Great Red Spot, a storm larger than Earth, has been raging for at least 300 years. Wind speeds in Jupiter's atmosphere can exceed 400 kilometers per hour, driven by the planet's rapid rotation and internal heat. Jupiter's influence extends far beyond its visible surface. Its powerful magnetic field, 20,000 times stronger than Earth's, creates radiation belts that would be lethal to any spacecraft that ventured too close without proper shielding. The magnetosphere extends millions of kilometers into space, reaching all the way to Saturn's orbit. This magnetic cocoon traps charged particles from the solar wind, creating auroras at Jupiter's poles thousands of times more powerful than Earth's northern lights. But Jupiter's most fascinating features might be its moons, the Galilean satellites. 4 large moons discovered by Galileo in 1610 are worlds in their own right. Io, the innermost moon, is the most volcanically active body in the solar system. Tidal forces from Jupiter constantly knead Io's interior, generating enough heat to keep its surface in a state of perpetual eruption. Io's volcanoes spew sulfur compounds into space, creating a torus of plasma that orbits Jupiter. Europa, Jupiter's second largest moon, might be the best place in the solar system to search for life beyond Earth. Beneath its icy crust lies a global ocean containing more water than all of Earth's oceans combined. Tidal heating from Jupiter keeps this ocean liquid despite Europa's distance from the Sun. Recent observations have detected water vapor plumes erupting from Europa's surface, suggesting that material from the subsurface ocean periodically breaks through the ice. If life exists in Europa's ocean, it would have to survive in complete darkness, deriving energy from chemical reactions rather than photosynthesis. On Earth, communities of organisms thrive around deep-sea hydrothermal vents without any sunlight, using chemicals dissolved in the water as their energy source. Similar ecosystems might exist in Europa's dark ocean. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It possesses its own magnetic field, the only moon known to have one. This magnetic field creates a mini magnetosphere that carves out a bubble within Jupiter's massive magnetic environment. Ganymede also likely has a subsurface ocean, making it another potential habitat for life. Callisto, the outermost Galilean moon, is heavily cratered, a record of 4 billion years of impacts. Unlike the other 3 large moons, Callisto shows little evidence of geological activity, Its surface appears ancient and unchanged, making it a valuable record of conditions in the early solar system. Saturn, often considered the most beautiful planet, is famous for its spectacular ring system. These rings, composed of countless particles of ice and rock ranging in size from grains of dust to house-sized boulders, extend hundreds of thousands of kilometers from the planet but are remarkably thin, typically only about 10 meters thick. The rings are not solid structures, but rather collections of individual particles, each in its own orbit around Saturn. The origin of Saturn's rings remains somewhat mysterious. Some scientists believe they formed when a moon ventured too close to Saturn and was torn apart by tidal forces. Others suggest the rings are the remnants of material left over from Saturn's formation. Recent observations by the Cassini spacecraft, which orbited Saturn from 2004 to 2017, suggest the rings might be relatively young, perhaps only a few 100 million years old. Saturn's moon Titan is one of the most fascinating worlds in the solar system. Larger than Mercury, Titan is the only moon with a substantial atmosphere. This atmosphere is thicker than Earth's, and composed mainly of nitrogen, with traces of methane and other hydrocarbons. Methane plays a role on Titan similar to water on Earth, cycling through the atmosphere as methane rain falls from methane clouds, filling methane lakes and seas. The Cassini spacecraft revealed that Titan's surface is covered with dunes, mountains, and vast plains of sand composed not of silicon but of organic compounds. Lakes of liquid methane and ethane dot the polar regions, making Titan the only world besides Earth known to have stable liquid on its surface. These liquid hydrocarbons might provide a medium for exotic forms of life based on chemistry completely different from terrestrial biology. Beneath Titan's icy crust, another ocean might exist, this one made of water. If so, Titan would harbour two separate environments where life might develop: the surface with its liquid methane, and a subsurface water ocean. The chemistry occurring in Titan's atmosphere and on its surface resembles what scientists believe may have occurred on early Earth before life began, making Titan a natural laboratory for studying prebiotic chemistry. Enceladus, a small moon only 500 kilometers across, surprised scientists when the Cassini spacecraft discovered enormous geysers erupting from its south pole. These plumes shoot water vapor and ice particles hundreds of kilometers into space, some of which escapes Enceladus's weak gravity and feeds Saturn's E-ring. The discovery of these geysers indicated that Enceladus has an ocean beneath its icy surface. Analysis of particles in the plumes revealed the presence of salt, silica, and organic molecules, suggesting that the subsurface ocean is in contact with Enceladus's rocky core. This contact could create hydrothermal systems similar to those found at the bottom of Earth's oceans, environments that could potentially support life. Enceladus has quickly become one of the top priorities for future missions searching for life beyond Earth. The discovery happened almost by accident. Michelle Dougherty and her team were analysing magnetic field data from Cassini's flybys of Enceladus. The readings showed something unexpected, as if Enceladus was a larger obstacle than it appeared. At first they thought it might be an error in the spacecraft's trajectory calculations, but the signature appeared on multiple flybys, indicating something real was happening. Dougherty travelled to the Jet Propulsion Laboratory to present her findings, nervous because changing the flyby would disrupt 6 years of mission planning. But the possibility of discovering a water vapour atmosphere was exciting enough that the majority of the team decided it was worth the risk. The gamble paid off. When Cassini made its close approach to Enceladus, all the instruments captured spectacular data. Instead of an atmosphere covering the entire surface, they found water vapour outgassing from the South Pole through cracks in the ice. The mission had discovered 3 of the 4 ingredients necessary for life: a heat source, liquid water, and organic material. Only time, the 4th ingredient, remained to be confirmed. The discovery transformed our understanding of where life might exist in the solar system. Uranus and Neptune, the ice giants of the outer solar system, remain among the least explored planets. Only one spacecraft, Voyager 2, has visited these distant worlds, flying past Uranus in 1986 and Neptune in 1989. Despite their brief encounters, Voyager's observations revealed fascinating characteristics about these strange planets. Uranus spins on its side, its axis tilted 98 degrees from vertical. This unusual orientation means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness as Uranus orbits the Sun. What caused this dramatic tilt? The most likely explanation is a massive collision early in Uranus's history, when a body roughly the size of Earth slammed into the planet and knocked it over. Neptune, the most distant planet, generates more internal heat than it receives from the Sun. This heat drives the fastest winds in the solar system, with storms racing through Neptune's atmosphere at speeds exceeding 2,000 kilometers per hour. The source of Neptune's internal heat remains mysterious, as the planet should have cooled off long ago given its age and distance from the Sun. Both ice giants have complex systems of moons and rings. Neptune's largest moon, Triton, orbits in the opposite direction to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton is one of the coldest objects in the solar system, with surface temperatures reaching -235 degrees Celsius. Despite this extreme cold, Triton shows evidence of geological activity. Nitrogen geysers erupt from its surface, carrying dark material high into the thin atmosphere before depositing it back on the ice. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies that extends from Neptune's orbit to about 50 astronomical units from the Sun. This region contains hundreds of thousands of objects larger than 100 kilometers across, remnants from the solar system's formation that never coalesced into planets. Pluto, once classified as the 9th planet, is one of the largest known Kuiper belt objects. The New Horizons spacecraft flew past Pluto in 2015, revealing a world far more complex and geologically active than anyone expected. Instead of a dead, cratered sphere, New Horizons found a world with nitrogen ice glaciers, mountains made of water ice as hard as rock at Pluto's frigid temperatures, and a haze-filled atmosphere extending hundreds of kilometers above the surface. Pluto's heart-shaped region, informally named Tombor Regio, contains a vast plain of nitrogen ice called Sputnik Planitia. This plain is constantly renewed through a process similar to convection, with warmer ice from below rising to the surface while cooler surface ice sinks. The timescale for this convection is roughly 500,000 years, meaning Pluto's surface is, in geological terms, quite young. The dwarf planet's atmosphere, though incredibly thin, shows complex chemistry. Methane in the upper atmosphere is broken apart by sunlight, creating a cascade of chemical reactions that produce complex organic compounds. These compounds fall as a dark reddish haze, coating Pluto's surface and giving it its distinctive coloration. Similar processes occur in Titan's atmosphere, suggesting that this type of chemistry might be common on cold worlds throughout the solar system and beyond. Charon, Pluto's largest moon, is so massive relative to Pluto that the two worlds orbit a common centre of gravity located in space between them. This makes Pluto and Charon effectively a binary system rather than a planet and moon. Charon's surface shows evidence of past geological activity, including canyons and smooth plains that might have formed when a subsurface ocean froze and expanded. Even further out beyond the Kuiper belt lies the Oort cloud, a spherical shell of icy bodies surrounding the solar system. This region, extending roughly halfway to the nearest star, contains trillions of cometary nuclei. Occasionally, gravitational perturbations from passing stars or the Milky Way's tidal forces nudge some of these objects into the inner solar system, where they become the long-period comets that grace our skies. Understanding our solar system helps us understand planetary systems around other stars. The techniques we use to study Mars's climate or Europa's ocean inform our search for habitable worlds orbiting distant suns. Every discovery in our cosmic backyard provides context for interpreting observations of exoplanets, worlds so far away that we can barely detect their existence. The complexity we see in our solar system, with its diverse worlds and intricate dynamics, suggests that planetary systems might be far more varied and interesting than early theories predicted. Each new mission, each new observation, reveals that the solar system remains full of surprises even after centuries of study. Quantum physics governs the behaviour of the smallest particles in the universe, operating according to rules that seem to violate common sense. At the quantum scale, particles can exist in multiple states simultaneously, can tunnel through barriers that should be impenetrable, and can influence each other instantly across vast distances. These phenomena, though strange, have been confirmed through countless experiments and form the foundation of modern technology. The story of quantum physics begins with light. In the early 20th century, scientists discovered that light behaves both as a wave and as a particle, depending on how you observe it. When light passes through two narrow slits, it creates an interference pattern on a screen behind them, a behavior that can only be explained if light travels as waves. But when you try to detect which slit the light passes through, the interference pattern disappears and light behaves like particles. This wave-particle duality extends to all matter, not just light. Electrons, atoms, and even large molecules can exhibit wave-like behavior under the right conditions. The larger an object becomes, the more difficult it is to observe these quantum effects, which is why everyday objects don't seem to exist in multiple places at once, or tunnel through walls. The uncertainty principle, discovered by Werner Heisenberg in 1927, states that you cannot simultaneously know both the precise position and precise momentum of a particle. The more accurately you measure one property, the less accurately you can know the other. This isn't a limitation of our measurement tools, but a fundamental feature of reality. At the quantum scale, particles simply don't have definite positions and momenta at the same time. This uncertainty manifests in surprising ways. Empty space isn't truly empty, but seethes with quantum fluctuations, virtual particles that pop into existence and annihilate each other in tiny fractions of a second. These fluctuations have measurable effects. They contribute to the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force caused by quantum fluctuations in the space between them. Quantum entanglement might be the strangest phenomenon of all. When two particles become entangled, measuring a property of one instantly affects the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance and argued that it proved quantum mechanics was incomplete. But decades of experiments have confirmed that entanglement is real. This doesn't mean information can travel faster than light. When you measure an entangled particle, you get a random result. Only by comparing your measurements with someone else measuring the other particle can you see the correlation. The information about what result the other person obtained still has to travel at the speed of light or slower, but the correlation itself is instantaneous, suggesting that at some deep level, space might not separate objects in the way we intuitively imagine. Quantum tunneling allows particles to pass through barriers that classical physics says should be impenetrable. An electron encountering a barrier has a small probability of appearing on the other side without having physically travelled through it. This phenomenon is essential for many processes in nature. Nuclear fusion in the Sun relies on quantum tunneling. Without it, the Sun's core wouldn't be hot enough for protons to overcome their electrical repulsion and fuse together. The quantum world also exhibits superposition, where particles exist in multiple states simultaneously until observed. The famous thought experiment of Schrödinger's cat illustrates this principle. A cat in a box with a quantum device that has a 50% chance of releasing poison exists in a superposition of alive and dead states until someone opens the box and observes the cat. This seems absurd for a cat, but for individual particles, superposition is routine. What constitutes an observation? This question leads to one of the deepest mysteries in physics. In quantum mechanics, the act of measurement causes a superposition to collapse into a definite state. But what counts as a measurement? Does it require a conscious observer, or does any interaction with the environment cause collapse? Different interpretations of quantum mechanics give different answers to these questions. The many worlds interpretation suggests that the universe doesn't choose one outcome when a measurement occurs. Instead, the universe splits into multiple branches, one for each possible outcome. In one branch, the cat is alive. In another, it's dead. Both outcomes occur, just in different non-interacting branches of reality. While this sounds like science fiction, some physicists argue it's the most straightforward interpretation of the mathematics. Quantum mechanics isn't just philosophical speculation, it enables much of modern technology. Transistors, the building blocks of computer chips, rely on quantum tunneling. Lasers work because of quantum properties of atoms and light. MRI machines use quantum spin to create detailed images of the inside of the human body. GPS satellites require corrections for both relativistic time dilation and quantum effects in their atomic clocks. The field of quantum computing promises to revolutionize information processing. Classical computers store information in bits that are either 0 or 1. Quantum computers use qubits that can be in superpositions of 0 and 1 simultaneously. This allows quantum computers to perform certain calculations exponentially faster than classical computers, potentially solving problems that would take conventional computers longer than the age of the universe. Building practical quantum computers presents enormous challenges. Quantum states are fragile and easily disrupted by interactions with the environment, a process called decoherence. Maintaining quantum coherence long enough to perform useful calculations requires isolating the system from all external influences while still being able to control and measure it. Despite these difficulties, progress has been rapid, with quantum computers now able to perform certain calculations that classical computers cannot match. Quantum cryptography uses entanglement to create communication channels that are theoretically impossible to eavesdrop on without detection. Any attempt to intercept the quantum keys used to encrypt messages would disturb the quantum states and alert the legitimate users to the security breach. Several quantum communication networks already exist, with longer-distance quantum communication satellites under development. The boundary between the quantum world and the classical world we experience remains fuzzy. Small objects clearly behave quantum mechanically, large objects clearly don't. But where exactly does the transition occur? Experiments have demonstrated quantum behavior in ever larger systems, from individual atoms to molecules containing thousands of atoms. Some scientists speculate that quantum effects might play a role in biological processes like photosynthesis or even consciousness, though these ideas remain controversial. One thing is certain: the quantum world operates according to its own rules that our intuition, evolved to deal with medium-sized objects moving at moderate speeds, finds deeply counterintuitive. Yet these rules are not just mathematical abstractions, they describe the actual behavior of the universe at its most fundamental level. Learning to think quantum mechanically means accepting that reality is far stranger than it appears. The moon holds a special place in human consciousness. It's the only other world that humans have walked upon, the closest celestial body, and Earth's constant companion through billions of years of history. Yet despite its familiarity, the moon continues to reveal secrets about its formation, evolution, and potential for future exploration. The leading theory for the moon's origin involves a catastrophic collision. About 4.5 billion years ago, when Earth was still young, a Mars-sized object called Theia slammed into our planet. The impact was so violent that it vaporized Theia and a large portion of Earth's mantle, ejecting an enormous amount of material into orbit. This debris gradually coalesced through gravitational attraction, forming the moon we see today. Evidence for this giant impact hypothesis comes from multiple sources. Moon rocks brought back by Apollo astronauts have chemical compositions similar to Earth's mantle but lack volatile elements that would have been lost in the heat of the collision. The Earth-Moon system has unusual angular momentum for its size, explained by the off-center impact. Computer simulations of such a collision produce moons with the right mass, orbit, and composition to match observations. The young moon was much closer to Earth than it is today, appearing enormous in the sky and creating tides hundreds of meters high. These massive tidal forces affected Earth's rotation and gradually pushed the moon into a higher orbit through a process called tidal acceleration. The moon continues moving away from Earth at a rate of about 3.8 centimeters per year, measured precisely using laser reflectors left on the lunar surface by Apollo astronauts. As the moon moved away, its effect on Earth's rotation diminished, but it still plays a crucial role. The moon's gravity stabilizes Earth's axial tilt, preventing wild variations that would create extreme climate changes. Without the moon, Earth's axis would wander chaotically over millions of years, dramatically affecting seasons and making the evolution of complex life more difficult. The moon's surface preserves 4 billion years of solar system history. Unlike Earth, where plate tectonics, erosion, and volcanic activity constantly renew the surface, the moon has remained geologically dead for billions of years. Craters from ancient impacts remain frozen in time, allowing scientists to study the bombardment history of the inner solar system. The lunar surface divides into two main regions, the bright highlands and the dark Maria. The highlands are older, heavily cratered terrain representing the moon's original crust. The Maria, Latin for seas, are vast plains of solidified lava that filled large impact basins billions of years ago. These dark patches create the familiar man-in-the-moon face visible from Earth. The Maria formed during a period of intense volcanic activity between 3.8 and 3 billion years ago. Massive impacts created basins that penetrated deep into the Moon's interior, allowing magma to well up and flood the basins with lava. As the Moon cooled, volcanic activity ceased, and no new Maria have formed for billions of years. Apollo astronauts collected nearly 400 kilograms of lunar rocks and soil. Analysis of these samples revealed the Moon's composition and history in extraordinary detail. The rocks are similar to Earth's in many ways, but completely dry, lacking the water-bearing minerals common in terrestrial rocks. Recent observations have complicated this picture, detecting water ice in permanently shadowed craters at the lunar poles and possible water molecules across the lunar surface. The discovery of lunar water ice has implications for future exploration. Water can be split into hydrogen and oxygen for rocket fuel or breathable air. It can shield against radiation or sustain crews for long-duration missions. The presence of water makes establishing a permanent lunar base significantly more practical than previously thought. The Moon experiences extreme temperature variations. In sunlight, the lunar surface can reach 127 degrees Celsius. In darkness, temperatures plunge to minus 173 degrees Celsius. This 200-degree swing occurs because the Moon has virtually no atmosphere to moderate temperatures or transport heat from sunny to shady areas. The lack of atmosphere also means that the lunar sky is always black, even during the day. Stars remain visible whenever the sun doesn't shine directly in your eyes. From the Moon's surface, Earth appears as a beautiful blue marble hanging motionless in the sky, never rising or setting because the Moon is tidally locked to Earth. This tidal locking occurred early in the Moon's history. The same gravitational forces that cause ocean tides on Earth also raised tides in the Moon's rocky interior. Over millions of years, these tidal forces slowed the Moon's rotation until it matched its orbital period, ensuring that the Moon always shows the same face to Earth. The far side of the Moon, never visible from Earth until spacecraft photographed it in the 1950s, differs dramatically from the near side. It has very few Maria, instead showing heavily cratered highlands. Scientists still debate why the two hemispheres are so different. One theory suggests that the near side formed with a slightly thinner crust, making it easier for lava to reach the surface and form Maria. Another proposes that the giant impact that created the South Pole Aitken Basin on the far side altered the Moon's thermal evolution. The Moon influences Earth in ways beyond tides and axial stability. The regular cycle of lunar phases may have influenced the evolution of biological rhythms. Many marine organisms time their reproductive cycles to lunar phases, suggesting that the Moon's gravitational influence has shaped life on Earth in subtle ways throughout evolutionary history. Future lunar exploration will likely focus on the poles, where permanently shadowed craters contain water ice, and some regions receive nearly continuous sunlight, providing ideal locations for solar panels. Several nations and private companies plan to establish lunar bases in the coming decades, using the Moon as a proving ground for technologies needed for Mars missions and a stepping stone for deeper space exploration. The Moon represents both our past and our future. It formed from the same violent processes that shaped Earth. It has been humanity's companion throughout our existence, influencing our calendars, myths, and sense of place in the cosmos. And it will likely be the first extraterrestrial body where humans establish a permanent presence, beginning our transformation into a truly spacefaring species. Pluto orbits in the distant reaches of the solar system, taking 248 years to complete one trip around the Sun. For most of that orbit, Pluto is the most distant planet from the Sun. But for 20 years in each orbit, Pluto actually passes inside Neptune's orbit, making Neptune briefly the outermost planet. Pluto will not pass inside Neptune's orbit again until the 2280s. The discovery that Pluto is just one of many large objects in the Kuiper belt led to its reclassification from planet to dwarf planet in 2006. This decision proved controversial, with many people feeling an emotional attachment to Pluto's status as the 9th planet. But the reclassification reflects our improved understanding of the solar system's structure, rather than any diminishment of Pluto's intrinsic interest. New Horizons revealed that Pluto is geologically active despite its small size and frigid temperatures. The mechanism driving this activity remains unclear. Pluto is too small to retain significant heat from its formation, and it doesn't experience strong tidal heating like Jupiter's moon Io. Some scientists propose that radioactive decay in Pluto's core might provide enough heat, while others suggest that slow convection in the nitrogen ice of Sputnik Planitia could power surface renewal. The dwarf planet's 5 known moons orbit in a complex dance. Charon, by far the largest, is so big relative to Pluto that the system's centre of mass lies between them rather than inside Pluto. The smaller moons, Styx, Nix, Kerberos, and Hydra, all likely formed from debris created when the impact that formed Charon scattered material into orbit around Pluto. These small moons behave strangely. Observations by the Hubble Space Telescope showed that some of them tumble chaotically rather than rotating steadily. This unusual behaviour results from their irregular shapes and the complex gravitational environment created by Pluto and Charon. For someone standing on one of these moons, the sky would slowly tumble around them, making celestial navigation challenging. The other dwarf planets in the Kyper belt await detailed exploration. Eris, slightly smaller than Pluto but more massive, orbits much farther from the Sun, taking 560 years to complete one orbit. Its surface, covered in methane ice, reflects nearly all the light that hits it, making Eris one of the brightest objects in the solar system, despite its small size and great distance. Makemake and Haumea, 2 other large Kuiper belt objects, have their own fascinating characteristics. Haumea spins faster than any other known object its size, completing one rotation every 4 hours. This rapid spin stretches Haumea into an elongated shape, like a football. It also has a ring system, making it one of only a few ringed objects beyond the gas giants. The small worlds of the outer solar system preserve clues about the solar system's formation. Unlike the terrestrial planets, which have been heated and reformed many times, these Xebeus bodies have changed little since they formed 4.6 billion years ago. Studying them gives us a window into the conditions and processes that prevailed in the early solar system. Future missions to explore these distant worlds face significant challenges. The journey takes years or decades, and solar panels become less effective at such distances from the Sun, requiring spacecraft to use nuclear power sources. Communication delays mean that spacecraft must operate autonomously for much of their mission. Despite these challenges, several missions to the outer solar system are in planning or development, promising to reveal more secrets of these mysterious worlds. Between the stars lies mostly empty space, but not complete emptiness. The interstellar medium, the material between star systems, consists of extremely diffuse gas and dust. On average, each cubic centimetre of interstellar space contains about 1 atom, compared to about 10 to the 19th atoms in a cubic centimetre of air at sea level on Earth. Despite this extreme thinness, the interstellar medium plays crucial roles in galactic evolution. Interstellar gas provides the raw material for new stars. Dust grains, though they comprise less than 1% of the interstellar medium's mass, play disproportionate roles in chemical reactions and in shielding dense clouds from starlight, allowing them to collapse and form new stars. The interstellar medium isn't uniform. It ranges from hot, diffuse gas with temperatures reaching millions of degrees, created by supernovae and stellar winds, to cold, dense molecular clouds with temperatures just 10 degrees above absolute zero. Between these extremes lie several other phases, each with characteristic temperatures, densities, and compositions. Cosmic rays, high-energy particles that travel through space at nearly the speed of light, contribute to the interstellar radiation field. These particles, mostly protons and atomic nuclei, are accelerated to tremendous energies by supernova shockwaves and other violent processes. Cosmic rays can penetrate matter deeply, ionizing atoms and molecules and contributing to the chemistry of the interstellar medium. The interstellar magnetic field, though incredibly weak by terrestrial standards, influences the motion of charged particles and shapes the structure of the interstellar medium on large scales. The field threads through the galaxy, following spiral patterns and creating complex three-dimensional structures that guide the flow of gas and the motion of cosmic rays. Interstellar dust, composed of tiny grains of silicates, carbon and ice, blocks and scatters starlight, creating the dark patches visible in images of the Milky Way. These dust grains also serve as surfaces where molecules can form. Hydrogen atoms meeting on a dust grain can combine to form molecular hydrogen, the most common molecule in space and the primary component of the dense clouds where stars form. Radio. Observations reveal that space is filled with a variety of molecules, over 200 different species identified to date. Some are simple, like water and carbon monoxide. Others are complex organic molecules, including amino acids, the building blocks of proteins. The presence of these molecules in interstellar space raises interesting questions about the origins of life, and whether organic chemistry occurred before planets formed. Occasionally, we can study interstellar material directly when it enters the solar system. In 2017, astronomers detected Oumuamua, an object from interstellar space passing through our solar system. Its unusual elongated shape and unexpected acceleration as it left the solar system generated intense interest and speculation. More recently, Comet Borisov, clearly identified as a comet from another star system, provided an opportunity to study interstellar material in more detail. These interstellar visitors represent only a tiny sample of the material between stars. Most interstellar objects passing through the solar system go undetected because they're too faint or too far from the sun when they pass through. Future surveys with more sensitive instruments and broader sky coverage should detect many more such objects, allowing us to study the composition and properties of material from other parts of the galaxy. The space between galaxies is even emptier than interstellar space. In the vast voids that occupy most of the universe's volume, the density drops to perhaps 1 atom per cubic meter or even less. These cosmic voids aren't completely empty though. They contain diffuse gas, dark matter, and occasional isolated galaxies or galaxy groups. The distribution of matter in the universe, with galaxies clustered along filaments surrounding vast empty voids, emerged from tiny density fluctuations in the early universe. Gravity amplified these small variations over billions of years, pulling matter into dense regions while draining it from the voids. The resulting cosmic web structure is one of the largest scale patterns in nature, extending across the observable universe. Light from distant objects travels through all this emptiness before reaching us. Along the way, it encounters tenuous clouds of gas that absorb specific wavelengths, leaving absorption lines in the spectrum. These absorption lines provide information about the composition, temperature, and motion of gas clouds billions of light-years away, giving us a window into conditions in the early universe. The universe continues expanding, stretching the space between galaxies. This expansion doesn't occur within galaxies or galaxy clusters, where local gravitational forces overcome the expansion. But on larger scales, the expansion dominates, gradually increasing the distances between galaxy clusters and making the universe ever more diffuse as time passes. In the far future, tens or hundreds of billions of years from now, this expansion will have carried distant galaxies beyond our cosmic horizon. They will recede faster than light can travel through the expanding space between us, making them forever invisible. Galaxies bound together in local groups will remain visible to each other, but the rest of the universe will fade from view, leaving each galaxy group as an island in an increasingly empty cosmos. For now, though, the universe remains rich with structure and activity. Stars are born, live their lives, and die in spectacular explosions. Galaxies merge and evolve. Black holes consume matter and release energy. The cosmos continues its grand evolution, playing out patterns set in motion nearly 14 billion years ago in the Big Bang's first moments. Understanding the universe requires accepting that emptiness is more common than substance, that the spaces between things are vaster than the things themselves. Yet these empty spaces aren't truly featureless. They're woven through with fields and forces, threaded with photons from ancient stars, and shaped by the invisible presence of dark matter and dark energy. The universe is vast beyond comprehension, yet we have learned to measure it, to probe its history and to predict its future. Our observations reach back to within a fraction of a second of the Big Bang itself. We can calculate the universe's age, map its large-scale structure, and understand the processes that created the elements in our bodies. This knowledge comes not from divine revelation, but from careful observation, mathematical analysis, and the scientific method applied over centuries by countless researchers. Each discovery builds on previous work, gradually constructing an ever more complete picture of cosmic reality. Many questions remain unanswered, but each generation pushes the frontier of knowledge further, revealing new wonders and deeper mysteries. As you rest tonight, remember that you're part of this vast cosmic story. The atoms in your body were forged in ancient stars. The patterns of neural activity in your brain follow laws discovered by observing distant galaxies. You are, quite literally, the universe becoming aware of itself, a temporary concentration of matter and energy complex enough to contemplate its own existence. The universe doesn't hurry. It unfolds according to its own timeless patterns, indifferent to human wishes and fears. Stars will continue burning their nuclear fuel, black holes will continue warping space-time, and galaxies will continue their slow evolutionary dance long after humanity has vanished. Yet for this brief moment in cosmic history, we exist to witness it all, and to marvel at the universe's beauty and strangeness. Rest now, knowing that the cosmos continues its eternal motion all around you, vast and mysterious and utterly unconcerned with human affairs, yet somehow giving rise to consciousness capable of understanding it. The universe is not here for us, but we are here because of it, products of 14 billion years of cosmic evolution, temporarily gathered together from stardust to think and feel and wonder at it all. Sleep well, traveller through space and time. The universe will still be here when you wake. The cosmos contains structures so vast that light takes hundreds of millions of years to cross them. These enormous formations, called galaxy superclusters, represent the largest gravitationally bound structures in the universe. Our own Milky Way resides within the Laniakea supercluster, a collection of over 100,000 galaxies spread across 500 million light-years. The Laniakea supercluster wasn't discovered until 2014, despite being our cosmic neighbourhood. The discovery came not from observing the galaxies directly, but from mapping their motions. Galaxies within Laniakea all flow toward a common gravitational centre called the Great Attractor, a massive concentration of matter whose exact nature remains somewhat mysterious due to its position behind the disk of the Milky Way. Beyond Laniakea lie other superclusters, each containing thousands or tens of thousands of galaxies. The Shapley supercluster, located about 650 million light-years away, is one of the most massive structures known in the nearby universe. Its enormous gravitational pull affects the motion of galaxies across billions of light-years, including our own. Between superclusters stretch the cosmic voids, enormous regions of space containing very few galaxies. The Bhuta's void, discovered in 1981, spans 330 million light-years and contains only about 60 galaxies where thousands would normally be expected. These voids aren't completely empty, but are significantly underdense compared to the rest of the universe. The large-scale structure of the universe resembles a three-dimensional spiderweb, with galaxies concentrated along filaments surrounding vast voids. This cosmic web arose from tiny density fluctuations in the early universe, amplified by billions of years of gravitational attraction. Computer simulations of cosmic evolution, starting from conditions shortly after the Big Bang and applying known physics, produce structures remarkably similar to what we observe. This agreement between simulation and observation provides strong evidence that we understand the universe's large-scale evolution. The simulations require including dark matter, which comprises about 85% of all matter. Without dark matter, simulations fail to produce the structures we see. This provides some of the strongest evidence for dark matter's existence, even though we haven't directly detected the particles that compose it. The distribution of matter across the universe is surprisingly uniform on the very largest scales. If you average over volumes larger than a few hundred million light-years, the density becomes nearly the same everywhere you look. This uniformity, combined with observations of the cosmic microwave background, supports the cosmological principle, the idea that, on large scales, the universe looks the same in all directions and from all locations. This principle has profound implications. It means that the physical laws we observe here on Earth apply throughout the cosmos. The light from distant galaxies follows the same rules as light in our laboratories. Gravity works the same way in distant superclusters as it does in our solar system. Chemistry in molecular clouds halfway across the universe produces the same molecules we find on Earth. The universe's large-scale uniformity seems to conflict with the obvious clumpiness we see around us. stars, planets, galaxies. This apparent contradiction resolves when we consider scale. On small scales, gravity has had time to amplify density fluctuations into distinct structures. On very large scales, there hasn't been enough time for gravity to create significant variations from the nearly uniform conditions of the early universe. Observations of distant quasars and galaxies allow us to study the universe's evolution over cosmic time. When we look at objects 10 billion light-years away, we see them as they were 10 billion years ago. The light has been travelling toward us for most of the universe's history. By comparing observations at different distances, astronomers can trace how galaxies, stars, and large-scale structures have changed over time. These observations reveal that the universe was quite different in the past. Early galaxies were smaller, bluer, and more irregular than modern galaxies. The rate of star formation was much higher when the universe was a few billion years old than it is today. Galaxy mergers and interactions were more common. The universe was, in many ways, a more violent and active place. As the universe expands, the wavelength of light travelling through it gets stretched. This cosmological redshift provides a direct measure of how much the universe has expanded since the light was emitted. The most distant galaxies observed have redshifts indicating the universe has expanded by a factor of more than 10 since their light began its journey toward us. The expansion of space itself carries distant galaxies away from us. This is different from objects moving through space. A galaxy 10 billion light-years away recedes from us faster than a galaxy 1 billion light-years away, even though both may have the same intrinsic velocities through space. The expansion of the space between us makes distant objects appear to recede at speeds proportional to their distance. At extreme distances, this recession can exceed the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Instead, the space between us and them is expanding. The observable universe has a definite edge, a cosmic horizon beyond which we cannot see, not because of any physical barrier, but because light from farther away hasn't had time to reach us yet. This cosmic horizon is currently about 46 billion light-years away, even though the universe is only about 13.8 billion years old. The difference arises because space has been expanding while light travels toward us. The most distant light we can observe comes from the cosmic microwave background, emitted when the universe was only 380,000 years old. This represents our ultimate observational limit for electromagnetic radiation. To probe earlier times, astronomers hope to detect gravitational waves from the Big Bang itself. These primordial gravitational waves, if detected, would provide a window into the universe's first fraction of a second, revealing conditions and processes that can never be studied through light. Several experimental efforts are underway to detect these faint signals, which would be imprinted on the cosmic microwave background's polarization pattern. The universe's expansion is accelerating, driven by dark energy, a mysterious component that comprises about 68% of the universe's total energy density. Dark energy behaves like a property of space itself. As the universe expands and new space is created, more dark energy comes into existence. This causes the expansion rate to increase over time rather than slow down as gravity would suggest. The nature of dark energy remains one of the deepest mysteries in physics. It could be Einstein's cosmological constant, a fixed energy density built into the fabric of space-time. It could be a dynamic field called quintessence that changes over time, or it could be a sign that our understanding of gravity needs modification on cosmic scales. Current observations don't distinguish between these possibilities, though they rule out many specific models. The accelerating expansion has dramatic implications for the universe's future. Distant galaxies will continue receding faster and faster, eventually crossing our cosmic horizon and disappearing from view. In the far future, only galaxies in our local group bound together by gravity will remain visible. The rest of the universe will have receded beyond the reach of any signal, leaving our cosmic descendants in an isolated island surrounded by empty space. Even our local group will not remain unchanged. In about 6 billion years, the Milky Way and Andromeda will complete their merger. Later, other local group galaxies may join the combined system. Eventually, after hundreds of billions of years, all the local group's galaxies will have merged into a single enormous elliptical galaxy, alone in an otherwise empty observable universe. Star formation will gradually decline as galaxies consume their gas supplies. The The last stars will form perhaps 100 trillion years from now. After that, the universe will enter an era dominated by slowly cooling stellar remnants, white dwarfs, neutron stars, and black holes. Even these objects will eventually decay or evaporate on timescales far longer than the current age of the universe. The ultimate fate of matter remains uncertain. If protons are stable, matter will persist indefinitely, though it will be spread ever more thinly as black holes evaporate through Hawking radiation. If protons eventually decay, as some theories suggest, even atomic nuclei will disintegrate, leaving only the lightest particles and radiation. In either case, the universe appears headed toward a state of maximum entropy, where no energy gradients exist and no complex structures can form or persist. These far-future scenarios, though speculative, follow logically from our current understanding of physical laws. They remind us that the universe we inhabit represents a brief moment in cosmic history, a time when conditions happen to allow the existence of stars, planets, and life. The universe was not always like this and will not remain like this. We live in a golden age of cosmic evolution, when structure and complexity reach their peak before the long decline into darkness and silence. Yet even in this grim future, the laws of physics will continue to operate. Conservation principles will still hold. Quantum mechanics will still govern particle behavior. The universe will remain comprehensible, even if there's no one left to comprehend it. The mathematical relationships that describe reality are timeless, existing independent of matter or energy or conscious observers. Our ability to understand these distant futures, to predict the universe's evolution across timescales that dwarf human history, represents one of science's greatest achievements. We can project our knowledge far beyond direct experience, testing our understanding against observations of the distant past and making predictions about the unobservable future. When these predictions prove correct, as they often do, we gain confidence that our models capture something real about the universe's operation. The study of cosmology, of the universe as a whole, has transformed from philosophical speculation to precision science in just a few generations. We can now measure the universe's age, composition, and geometry with remarkable accuracy. We understand its history from the first fraction of a second to the present day. We can identify the physical processes that shaped cosmic evolution and predict how those processes will unfold over incomprehensible spans of future time. This knowledge comes with a certain existential weight. Understanding the universe's vastness and our tiny place within it can feel overwhelming. We are microscopically small, existing for an eye blink on cosmic timescales, inhabiting an average planet around an average star in an average galaxy in an average region of space. Our entire civilization, all of human history, occupies a moment so brief as to be essentially instantaneous on cosmic scales. Yet we're also the universe's way of knowing itself. The atoms in our bodies were forged in stellar cores. The laws we discover through observation and experiment govern all of reality. When we study the universe, we are, in a very real sense, the universe studying itself. This self-awareness, this capacity for understanding may be rare in the cosmos. It may even be unique. We don't know. The question of our place in the universe remains open. Are we alone, or does life exist elsewhere? Is intelligence common or rare? Have other civilizations arisen, asked these same questions, and gazed out at the same cosmos we observe? We cannot yet answer with certainty. Our searches for extraterrestrial intelligence have found no clear signals. Our studies of exoplanets suggest that Earth-like worlds are common, but we haven't detected any signs of life beyond our planet. The silence might mean we're alone, at least in our cosmic neighborhood. It might mean that life is common, but intelligence or technological civilization is rare. It might mean that civilizations exist but don't communicate in ways we can detect. Or they existed in the past or will exist in the future, but not during the tiny time window when we're looking. Each possibility carries its own profound implications for understanding our place in the cosmos. If we are alone, it makes Earth and human civilization precious beyond measure. We would be the only instance of matter becoming self-aware in all the vast cosmos, at least in our observable corner of it. The responsibility to preserve and expand consciousness would rest entirely with us. Every extinction, every loss of knowledge or capability would be a tragedy on cosmic scales. If life is common, but we're among the first technological civilizations to arise, we may be in a position to shape the galaxy's future. Our choices might determine whether intelligence spreads through the cosmos or remains confined to a single world. The decisions we make in the next few centuries could echo across millions of years. If many civilizations have come before us, their absence in our observations becomes puzzling. Where are they? Why haven't they left obvious traces? The Fermi paradox, the apparent contradiction between high estimates of the probability of extraterrestrial civilizations and the lack of evidence for them, remains unresolved. Perhaps intelligence inevitably self-destructs. Perhaps interstellar travel is harder than we imagine. Perhaps we're not looking in the right way. Or perhaps the universe is simply too vast for civilizations to find each other easily. Space is unimaginably large. Even travelling at the speed of light, it would take hundreds of thousands of years to cross our galaxy. If civilizations are separated by thousands or millions of light years, they might exist but never make contact. We could be shouting into the darkness, but our voices haven't reached anyone yet, and their messages haven't reached us. These questions about life and intelligence in the universe connect to our deepest concerns about meaning and purpose. Science can tell us how the universe works, but it cannot tell us why it exists or what we should do with our existence. Those questions remain in the realm of philosophy, ethics, and personal choice. Each person must find their own answer. What we can say with certainty is that we are part of an extraordinary cosmic story. The same processes that formed galaxies and stars also formed Earth and gave rise to life. The same laws that govern distant quasars also govern our cells. We are made of stardust, literally. Every atom heavier than hydrogen in your body was forged in a star that exploded before our solar system formed. The carbon in your muscles, the calcium in your bones, the iron in your blood, all came from stellar nucleosynthesis. When you breathe, you inhale atoms that have cycled through countless living things over billions of years. You're a temporary pattern in matter that will eventually dissolve and reform into new patterns. Your atoms will persist, recycled through Earth's biosphere, long after your consciousness has ceased. This perspective can seem nihilistic, reducing human existence to mere physics and chemistry. But it can also inspire awe. We are the universe's way of experiencing itself, of transforming matter and energy into thought and feeling. For a brief time, some atoms have arranged themselves into patterns complex enough to look out at the cosmos and comprehend it. That's remarkable, however it came about. The universe didn't need to be comprehensible. Physical laws didn't need to follow mathematical patterns that minds like ours could discover. Yet they do. The universe operates according to rules, and those rules are, at least in principle, understandable. This mysterious relationship between human consciousness and cosmic reality deserves wonder, regardless of your philosophical or religious views. Sleep comes as a gentle release from waking thoughts. Your body relaxes, your breathing slows, and consciousness gradually fades. While you sleep, the universe continues its eternal dance. Stars burn, galaxies turn, planets orbit in their ancient paths. Nothing pauses for human rest. The cosmos proceeds according to its timeless patterns, utterly indifferent to the concerns of any individual consciousness, yet you are connected to all of it. The same forces that shape galaxies also shape you. Gravity holds you to Earth's surface. Electromagnetic forces bind the atoms in your body. The weak nuclear force allows the sun to shine, providing the energy that powers all life. The strong force holds atomic nuclei together, preventing matter from flying apart. These four fundamental forces, operating according to precise mathematical laws, govern everything from subatomic particles to superclusters of galaxies. Your existence requires incredibly specific conditions. Change the strength of any fundamental force by even a small percentage, and the universe would be very different, probably unable to support life as we know it. The constants of nature appear to be finely tuned for the emergence of complexity. Whether this fine-tuning reflects design, chance, or something else remains a matter of debate, but the fact of it is undeniable. In a real sense, the universe must be the way it is for you to be here observing it. This anthropic principle doesn't explain why the universe has its particular properties. but it reminds us that our existence provides evidence about cosmic conditions. In a universe hostile to life, no one would be around to observe that hostility. We necessarily find ourselves in a universe capable of producing observers like us. Rest in this knowledge. You're not separate from the cosmos, but part of it. A temporary concentration of matter and energy complex enough to look back at the universe and wonder. Your atoms have existed for billions of years, and will exist for billions more, recycled endlessly through stars and planets, and perhaps other living things. The pattern that is you is temporary, but you are made of eternal stuff. The night deepens. Somewhere, stars are being born in clouds of gas and dust. Somewhere, massive stars are dying in supernova explosions, forging heavy elements and seeding the cosmos with the raw materials for new worlds. Somewhere, black holes are consuming matter, warping space-time beyond recognition. Somewhere, planets orbit in the habitable zones of distant stars, perhaps harbouring life forms contemplating their own existence. All of this happens now, simultaneously, in the vast universe. The present moment contains countless events separated by distances so vast that their light will take millions or billions of years to reach us. When we observe distant galaxies, we see them not as they are now, but as they were when their light began its journey toward us. The universe we observe is a patchwork of different eras, layered by distance and time. This strange property of light and distance means that in principle, every moment of the universe's history still exists somewhere in space, preserved in light travelling outward from the events that created it. If you could somehow travel faster than light and overtake the light from Earth that's currently racing through space, you could observe Earth's past directly, watching history unfold again. Of course, faster-than-light travel appears to be impossible according to our current understanding of physics, but the thought experiment illustrates how the universe's past is in some sense still present, encoded in light. Your own past similarly exists in principle, recorded in light that has left Earth and is now travelling through space. Images of you from years ago are currently passing distant stars, continuing outward toward the cosmic horizon. In this odd way, your younger self still exists out there in the universe, frozen in ancient light. Every moment you've lived has left this luminous echo, travelling forever through the void unless absorbed by dust or gas, or someday captured by an impossibly distant observer. These reflections may seem strange or unsettling. They violate our intuitive sense of time as a river flowing in one direction, with the past definitely gone and the future not yet formed. But relativity teaches us that past, present and future all exist in a four-dimensional space-time, with our movement through time creating the illusion of change. Every moment you've experienced still exists as a point in space-time, as real and present as this moment, just located at different temporal coordinates. If this is true, then in some sense you never truly disappear. Every moment of your existence remains eternally present in space-time, accessible in principle to any observer at the right location with the right velocity. The pattern of atoms and energy that comprises you at this moment is just one cross-section of a larger four-dimensional structure extending through time. You're not a thing but a process, a pattern that persists and changes, a melody rather than a note. Let these thoughts carry you deeper into rest. The universe is stranger and more wonderful than everyday experience suggests. You're part of something vast and ancient and ongoing, a brief spark of awareness in an ocean of matter and energy, a temporary interruption in entropy's slow victory. But while you exist, you get to experience it all, to feel and think and wonder. That's gift enough, however briefly it lasts. The universe will forget you eventually. Entropy ensures that all patterns dissolve given enough time. But for now you are here, aware, part of the cosmos awakening to itself. Rest in that knowledge. Let the vastness hold you. You're floating through space on a planet, rotating slowly under stars that have shone for billions of years. Everything is in motion, everything is changing, and you are part of that endless dance. The silence between thoughts grows longer. Awareness begins to dissolve into something quieter, deeper. The boundary between self and universe softens. Sleep approaches on gentle footsteps, bringing the daily small death that consciousness requires. Tomorrow you'll wake, memories mostly intact, ready to continue the brief spark of awareness you call your life. But for now, let go. The universe will still be here when you return. Breathe slowly. Feel the weight of your body against the surface beneath you. The Earth holds you gently, its gravity and embrace that has never faltered since your birth. That same gravity shapes galaxies, guides planets, and keeps the sun burning in its slow fusion fire. You're held by the same force that structures the cosmos. You've never been separate, never been alone. Everything that exists is connected through forces and fields, through space and time, through the flow of energy and the evolution of patterns. You are one pattern among countless others, unique in its details but following the same fundamental laws as everything else. Your thoughts arise from electrochemical processes that obey the laws of physics. Your feelings emerge from neural patterns shaped by evolution and experience, even consciousness, that most intimate and seemingly special phenomenon is somehow a product of ordinary matter following ordinary rules. How matter arranged just so can give rise to the inner world of experience remains mysterious. No one fully understands how neurons firing in patterns create the sensation of redness, the feeling of joy, or the sense of self. The hard problem of consciousness, as philosophers call it, persists despite centuries of investigation. But whatever consciousness is, it emerges from the physical universe. It is not separate from matter and energy, but somehow constituted by them. You are the universe's improbable gift to itself, matter becoming aware of matter, energy contemplating energy, patterns recognizing patterns. This self-awareness might be common in the cosmos, or it might be vanishingly rare. We don't yet know. But we know it exists here, in you, in this moment. The universe looks out through your eyes and knows itself, however briefly, however partially. Rest now. The searching can wait. The questions will still be there tomorrow. For now, let consciousness dissolve back into the darkness from which it emerges each morning. Sleep is practice for the longer dissolution that awaits us all eventually, but that's far away. For now, just rest. The universe holds you. You've never left home. You've always been part of this, will always be part of this in one form or another, until the end of time itself. And even then, even after the last star has burned out and the last black hole has evaporated and entropy has claimed its final victory, the patterns you embodied will have been real. They will have happened. Nothing can take that away. Your existence, brief though it may be on cosmic scales, is permanently woven into the fabric of space-time. You cannot be erased, only transformed. Drift now into dreams. The universe dreams through you, processing the day's experiences, consolidating memories, repairing cellular damage, preparing for tomorrow's continuation. Your brain remains active, generating bizarre narratives from random neural firing, trying to make sense of patterns that have no external referent. Dreams may seem strange, but they're just your mind practicing its basic function. Finding meaning in patterns, creating stories from fragments, imposing order on chaos. Everything you are happens in 3 pounds of wet neural tissue, electrical and chemical signals racing along connections forged by genetics and experience. Your entire inner world, all your memories and hopes and fears, exist as patterns in this biological computer. When those patterns stop, you stop. This knowledge can be frightening or peaceful, depending on your perspective, but it's simply true, as far as anyone can tell. The universe has given you this moment. All the moments you've had, all the moments you'll have, are gifts from a cosmos that didn't need to produce consciousness but did anyway. You didn't ask to exist, but here you are, aware and alive, at least for now. Make of that what you will. The universe offers no instruction manual, no clear purpose, no evident design. You must create your own meaning from the raw material of existence. That freedom can be terrifying or liberating. You're not constrained by cosmic purpose because there may not be one. You're free to choose your values, your goals, your relationships, your path through life. The universe won't judge your choices. It will simply continue, indifferent and magnificent, operating according to its timeless laws. But others will be affected by your choices. In this web of interconnection, your actions ripple outward, affecting other people, other living things, shaping the future in small or large ways. This gives life meaning and moral weight even in an indifferent universe. How you treat others matters. What you create or destroy matters. Not to the cosmos, perhaps, but to the conscious beings who will experience the consequences of your actions. Choose kindness when possible. Choose creation over destruction. Choose understanding over ignorance. Choose connection over isolation. These are not cosmic laws, but human values, hard-won from centuries of philosophical and ethical thought. The universe doesn't care whether you follow them, but you should care, because you're part of the human story, and that story continues only if each generation chooses to sustain it. Let these thoughts fade now. Moral responsibility is for waking hours. Sleep requires release, surrender, letting go of the burdens of consciousness. The world will still be there tomorrow, with all its beauty and terror, all its joy and suffering. You can pick up your responsibilities again then. For now, rest. You've earned it simply by existing, by making it through another day of the strange adventure called life. The darkness is complete now. Thoughts become fragmentary, disconnected. The boundary between waking and sleeping blurs. Soon you'll cross over entirely into dreams, and for the next few hours, you'll experience a different kind of consciousness, unconstrained by logic or physics, free to wander through impossible landscapes and encounter people who don't exist. Dreams are strange gifts, these nightly journeys into constructed realities. They serve functions we don't fully understand, processing emotions, consolidating learning, perhaps even solving problems that the waking mind cannot crack. But whatever their purpose, they are yours alone, private theatre performances with an audience of one. And then, after hours that will seem like minutes, you'll wake again. Consciousness will return, memory mostly intact, ready to experience another day of existence. The cycle continues, day after day, year after year, until eventually it stops. But that's not tonight. Tonight is just for rest. The universe spins on through the void. Stars burn, galaxies collide, black holes consume, life evolves, consciousness awakens, contemplates and returns to dust. The pattern repeats across billions of years, will repeat for billions more. You're one tiny instance of this pattern, unique in details but universal in kind. Rest well, small consciousness. You've been brave today simply by continuing to exist, by bearing the burden of awareness in an uncertain universe. Tomorrow you'll be brave again, but tonight you can rest. The cosmos continues without your vigilance. You are permitted to sleep, to surrender, to let go. The last thought fades. Awareness dissolves into the deeper currents of sleep. The universe proceeds without witness, at least from you, though countless other consciousnesses remain scattered across the cosmos, each perceiving their own small corner of reality. Together, all awareness constitutes the universe's attempt to know itself, a process that's been ongoing for billions of years and will continue for billions more. But you don't need to worry about that now. Your part in it can wait until morning. For now, just this: darkness, warmth, the slow rhythm of breathing, and the eternal mystery of existence continuing on without need of understanding. Good night, starborn traveller. Rest in the knowledge that you're exactly where you belong, exactly what you should be, a temporary pattern of matter and energy that has somehow learned to wonder at its own existence. The universe holds you gently in its vast indifference, and that is enough. Time flows differently when you release your grip on it. Minutes and hours lose their boundaries. The present moment expands to fill all available space. You exist in an eternal now, unchanging even as everything changes around you. This paradox lies at the heart of conscious experience. You're always in the present, yet the present is always slipping into the past, always becoming something you can never quite grasp. Physicists tell us that time might not flow at all. Einstein's equations treat time as just another dimension, no different in principle from the three spatial dimensions. The past, present and future all exist simultaneously in the four-dimensional structure of space-time. Our sensation of time flowing, of moving from past through present toward future, might be an illusion created by the way consciousness processes information. If this is true, then everything that has ever happened or will ever happen already exists in the eternal structure of space-time. Your birth and death are both already there, fixed points in the four-dimensional map of reality. You're not moving through time so much as your consciousness is illuminating different slices of a static structure, like a spotlight moving across a landscape that exists complete and unchanging. This block universe view of time feels wrong to our intuitions. We experience change. We remember the past but not the future. We feel that we make choices that alter what happens next. Yet physics offers no clear distinction between past and future at the fundamental level. The laws governing particles work equally well, whether time runs forward or backward. The arrow of time, the distinction between past and future, emerges only when we consider large collections of particles and the statistical laws of thermodynamics. Entropy, the measure of disorder in a system, always increases over time. This is the second law of thermodynamics, one of the most robust principles in physics. A broken glass doesn't spontaneously reassemble. Heat flows from hot to cold, never the reverse. These irreversible processes give time its direction, creating the distinction between past and future that we experience so vividly. But why does entropy increase? The answer lies in probability. There are many more ways for a system to be disordered than ordered. A broken glass represents one of countless possible arrangements of glass shards. An intact glass represents a very specific, highly ordered arrangement. Random processes tend to move systems from unlikely ordered states to likely disordered states, creating the arrow of time we observe. The early universe was in an extremely low entropy state, highly ordered and uniform. Everything since has been a gradual slide toward higher entropy, toward disorder and heat death. The formation of stars, galaxies and life are temporary local decreases in entropy, paid for by larger increases elsewhere. When the sun fuses hydrogen into helium, it creates order in the form of heavy elements, but it releases heat that increases the entropy of the surrounding space by a larger amount. Your existence represents a local decrease in entropy. Your body maintains a highly ordered state, with specific molecules in specific places performing specific functions. But this order is purchased through metabolism, through consuming food and releasing heat. The net effect of your life is to increase the universe's total entropy, contributing infinitesimally to the cosmic slide toward disorder. This might sound depressing, but it's simply the price of being a complex structure in an evolving universe. Order can exist temporarily, locally, but it cannot last forever. Eventually, entropy wins. But eventually means trillions upon trillions of years, timescales so vast that they're essentially meaningless to creatures who live for decades. For now, for the brief moment in cosmic history when we exist, order and complexity are possible. Stars shine, galaxies spiral, life evolves, minds think. This golden age will last for billions of years to come, even though it represents a tiny fraction of the universe's total lifetime. We are fortunate to exist during this narrow window when the universe is neither too young and chaotic nor too old and cold for complexity to flourish. The atoms in your body have their own history, stretching back billions of years. Every carbon atom was forged in the core of a star that lived and died before our sun was born. Every oxygen atom you breathe was created when that star exploded, scattering its enriched ashes into space. These atoms drifted through molecular clouds, were incorporated into the nebula that formed our solar system, condensed into Earth, and eventually became part of living organisms. Your atoms have been recycled countless times. Some were once part of ancient bacteria. Some were dissolved in primordial seas. Some were locked in rocks deep underground. Some were carried on the wind as dust. They've been part of plants, animals, rain, rivers, and mountains. Each atom has an unimaginably long history before becoming temporarily part of you, and when you die, those atoms will continue their journey. They'll be returned to Earth, incorporated into soil, taken up by plants, eaten by animals, breathed by future humans. The atoms that comprise you at this moment will be scattered across the biosphere, becoming part of thousands of future organisms. In this way, you will quite literally live on, not as a conscious entity, but as matter recycled endlessly through the web of life. This cycle of death and renewal has been operating for billions of years on Earth. every organism that has ever lived has contributed its atoms back to the pool. The carbon in your cells might have once been part of a dinosaur or a trilobite, or bacteria from Earth's earliest eras. You're made of the same stuff as everything that has ever lived, rearranged in a pattern that briefly creates the illusion of being separate. But you are not separate. You are continuous with the rest of life, connected through shared ancestry that extends back to the first self-replicating molecules. Every living thing on Earth shares a common ancestor, some primitive cell that lived billions of years ago. We are all cousins, all branches of the same tree of life, all made of the same basic components following the same basic biochemistry. This unity extends beyond life to include all matter. The atoms in rocks and oceans and air are the same kinds of atoms that make up your body, just arranged differently. The distinction between living and non-living is real, but not absolute. Life is simply matter organized in certain specific ways, following certain specific patterns capable of maintaining itself and reproducing. The boundary is fuzzy, with viruses and prions occupying an ambiguous zone between clearly living and clearly non-living. What makes you conscious? What creates your inner experience remains mysterious despite all our scientific knowledge. We understand increasingly well how brains work, how neurons process information, how memories form and decisions get made, but we still don't know how or why these physical processes give rise to subjective experience, to the felt quality of being someone, of experiencing sensations and emotions and thoughts. This explanatory gap, the hard problem of consciousness, persists despite centuries of philosophical and scientific investigation. Perhaps it will eventually yield to neuroscience as we map the brain in ever greater detail. Perhaps it requires new physics we haven't discovered yet. Perhaps it's a category error, asking the wrong kind of question. Or perhaps consciousness is fundamental to the universe, a basic feature of reality like mass or charge. Panpsychism, the idea that consciousness is a fundamental property of matter, has been proposed by various philosophers and scientists. In this view, even elementary particles have some rudimentary form of experience, and complex consciousness emerges when many particles organize into brains. This sounds strange, but it solves the hard problem by making consciousness ubiquitous, rather than emergent. Of course, it raises new questions about what it's like to be an electron, or how particle consciousness combines into human consciousness. Most neuroscientists reject panpsychism, believing consciousness emerges from complex information processing in brains without requiring any new physics. The integrated information theory proposed by Giulio Tononi attempts to quantify consciousness based on how integrated and differentiated information is within a system. In this framework, consciousness is a spectrum rather than an all-or-nothing property, with different systems having different degrees of consciousness depending on their information structure. These theories remain speculative, difficult or impossible to test empirically. The private nature of consciousness means we can never directly observe someone else's inner experience. We can only infer it based on behavior and reports. This creates an inherent limitation in studying consciousness scientifically. You can be certain of your own consciousness, but can never be absolutely certain that others are conscious rather than philosophical zombies, beings that behave like conscious entities but have no inner experience. Of course, this extreme skepticism isn't practically useful. We reasonably infer that other humans are conscious because they're similar to us and report experiences like ours. We extend this assumption to animals, at least those with complex nervous systems, though with less certainty. Where consciousness begins or ends in the animal kingdom remains debated. Mammals clearly seem conscious. Fish and insects less clear. Plants and bacteria, probably not, though some scientists argue for a broader definition. These questions matter for ethics. If animals are conscious, if they experience pain and pleasure, then we have moral obligations toward them. If future artificial intelligences become conscious, they too would deserve moral consideration. Conversely, if some entities that seem conscious actually aren't, our moral obligations differ. Unfortunately, we lack clear criteria for determining whether something is conscious, making these ethical questions difficult to resolve. Your own consciousness will end. Death extinguishes awareness permanently as far as anyone can tell. The pattern of neural activity that creates your sense of self will stop, and with it, all experience will cease. This cessation is the most fundamental fact about existence for mortal beings. everything you do, every choice you make, occurs in the shadow of eventual extinction. Different philosophical and religious traditions respond to this mortality in different ways. Some promise afterlives where consciousness continues in different realms. Some propose reincarnation, consciousness returning in new forms. Some embrace extinction, finding freedom in the idea that death ends all suffering. Science can't rule out all these possibilities definitively, but it finds no evidence for consciousness continuing after brain death. When the brain stops functioning, the pattern that constituted you dissolves, memories vanish, personality dissolves, the sense of being someone located in a particular body with a particular history evaporates. What remains is just matter, atoms that will be recycled into new patterns. The information that made you uniquely you is lost, scattered beyond recovery as entropy increases and patterns degrade. This might be frightening or comforting depending on your perspective. You will not suffer death because you will not exist to experience it. As Epicurus argued, death is nothing to us, since when we exist, death is not yet present, and when death is present, then we do not exist. The fear of death is really fear of dying or fear of non-existence, but non-existence itself cannot harm you because there's no you present to be harmed. Many fear not death itself, but the process of dying, which might involve pain, fear, or loss of dignity. These are legitimate concerns, different from the metaphysical question of whether death is bad. A quick, painless death in sleep differs greatly from prolonged suffering. Modern medicine increasingly allows people to die with less pain, though questions about end-of-life care and euthanasia remain ethically complex. Others fear death because of attachments to life, to people they love, to experiences they want to have, to projects they want to complete. Death means severing all these connections, leaving things unfinished. This fear makes sense given how much we invest in relationships and long-term goals. Death represents ultimate loss, the end of all possibility. Yet death also gives life meaning and urgency. If we lived forever, decisions would lack weight. We could always try again later, delay indefinitely, put off difficult choices. Mortality forces us to prioritize, to decide what matters most, to accept that we cannot do everything. The finite nature of existence creates the conditions for meaning. Different people find meaning in different ways, some through relationships, connecting deeply with others, some through creation, making art or building things that outlast them, some through understanding, learning about the world and expanding human knowledge, some through service, helping others and reducing suffering, some through experience, seeking pleasure and avoiding pain, some through transcendence, connecting with something larger than themselves. None of these paths is universally correct. The universe provides no instruction manual for how to live. You must discover or create your own meaning from the raw material of existence. This freedom can be overwhelming, but it's also liberating. You're not constrained by cosmic purpose because there may not be one to constrain you. The existentialists emphasize this freedom and the responsibility that comes with it. We are condemned to be free, as Sartre put it, unable to escape the necessity of choosing how to live. Even refusing to choose is itself a choice. We cannot defer to external authority or divine command because we must ultimately interpret and decide whether to follow such guidance. Authenticity means accepting this responsibility and making choices based on our own understanding rather than blindly following others. But absolute freedom can lead to paralysis or nihilism. If nothing matters objectively, why choose one path over another? The existentialists responded that while the universe may not care about our choices, we care, and that's enough to ground meaning. What matters to conscious beings matters, period, even if it doesn't matter cosmically. The love you feel, the beauty you experience, the suffering you endure, these are real and significant, regardless of the universe's indifference. Moreover, we don't choose in a vacuum. We're embedded in communities shaped by cultures, born into circumstances we didn't choose. These constraints and connections limit our freedom, but also provide context and shared meaning. We find meaning not only through individual choice, but through participation in traditions, relationships, and communities that existed before us and will continue after we're gone. You are a node in vast networks of connection, influencing and influenced by countless others. Your choices ripple outward in ways you cannot fully predict or control, A kind word might change someone's day, which changes their decisions, which affects others, creating cascades of consequence that eventually become impossible to trace. You participate in shaping the future, however small your contribution. This interconnection means that individual and collective good are intertwined. What benefits the community can benefit you, and vice versa. Ethical systems across cultures recognize this, though they emphasize different balances between individual and collective welfare. Finding this balance remains an ongoing challenge as we navigate increasingly complex social and global problems. The great challenges facing humanity, climate change, nuclear weapons, pandemics, artificial intelligence, require collective action at unprecedented scales. Individual choices matter but cannot solve these problems alone. We need cooperation, coordination, institutions that can implement solutions beyond what any person or small group can achieve. This requires trust, shared understanding, and willingness to constrain individual freedom for collective benefit. Yet history shows that humans can cooperate when necessary. We've built civilizations, created technologies, explored the world and beyond. We've developed art, music, literature, philosophy, science. We've reduced violence, extended lifespans, increased material prosperity for billions. These achievements required countless individuals working together across generations, building on what came before. You are heir to this accumulated human effort. The language you speak, the concepts you think with, the technologies you use, all were created by others and passed down to you. You stand on the shoulders of giants, able to see farther because of their work, and you will contribute, however small your addition, to the inheritance passed to future generations. This continuity across generations creates meaning that transcends individual mortality. You may die, but humanity continues. Your contributions, genetic and cultural, blend into the ongoing stream of human existence. Children carry genes from parents and grandparents stretching back through deep time. Ideas spread from mind to mind, evolving and combining in new forms. The pattern that was you will dissolve, but you will have influenced the patterns that follow. Unless, of course, humanity itself ends. We are not guaranteed survival. Our species might go extinct through our own actions or external catastrophe. The universe contains many dangers: asteroid impacts, supervolcanic eruptions, nearby supernova or gamma-ray bursts, and we pose dangers to ourselves through nuclear war, biological weapons, environmental collapse, or unforeseen consequences of future technologies. The probability of human extinction this century is debated, with estimates ranging from negligible to alarmingly high depending on which risks you emphasize and how you calculate. Existential risk researchers argue that reducing extinction risk should be a major priority, since losing humanity would foreclose all future potential value. Even small reductions in extinction probability could be worthwhile given the vast number of future lives at stake. But whether humanity survives or not, the universe will continue. Stars will keep burning, galaxies will keep evolving, black holes will keep consuming matter. The cosmos is indifferent to our fate. This can feel lonely and frightening, or it can feel liberating. We are free precisely because the universe doesn't care what we do. We can create our own meanings, our own values, our own purposes without cosmic constraints. The night deepens around you now. Thoughts become slower, more fragmentary. The boundary between waking and sleeping grows thin. Soon you'll cross over entirely, surrendering consciousness to the strange world of dreams. But before you do, rest in this knowledge. You are part of an ancient pattern, matter temporarily organized into awareness, experiencing the universe from within. This pattern has existed for billions of years in various forms. Life emerged on Earth nearly 4 billion years ago, perhaps earlier. It has survived mass extinctions, adapted to changing environments, evolved into millions of species. You represent one tiny branch of this great tree, one momentary expression of life's ability to persist and complexify, despite entropy's universal pull. Your existence required an improbable chain of events. Your parents had to meet. Their parents had to meet. This chain extends back through thousands of generations, through all your ancestors who survived long enough to reproduce, through hominids and earlier primates and earlier mammals, back to the first vertebrates, the first multicellular organisms, the first cells. Break any link in this chain, and you wouldn't exist. Moreover, Earth had to remain habitable for billions of years. The sun had to shine steadily. The planet's orbit had to remain stable. The magnetic field had to protect the atmosphere from solar wind. Plate tectonics had to recycle nutrients. The moon had to stabilize Earth's rotation. Any of these factors going wrong could have prevented life from evolving or caused its extinction. Beyond Earth, conditions across the universe had to allow for your existence. The physical constants had to fall within the narrow ranges that permit chemistry and stable atoms. The early universe had to have density fluctuations that grew into galaxies. Stars had to form, live, and die, creating and dispersing heavy elements. The particular galaxy cluster, galaxy, star system, planet, had to be suitable. From one perspective, you're incredibly improbable, a one in countless trillions occurrence that required the entire history of the universe to unfold in exactly the way it did. From another perspective, given the vastness of the universe and the long time available, something like you was perhaps inevitable somewhere, somewhen. The universe is so large that even extremely improbable events become likely when considered across all of space and time. Which perspective is correct? Both, perhaps. You are unique and unrepeatable as a specific individual with your exact genetics and experiences, but the general category of conscious beings might be common in the universe, with countless other individuals as unique as you existing on distant worlds, experiencing their own brief moments of awareness before returning to dust. We don't know if we're alone. We haven't detected any clear signs of other intelligent life despite decades of searching. The silence might mean we're the first technological civilization to arise in our cosmic neighborhood, or it might mean others existed but left no traces we can detect, or they communicate in ways we haven't recognized, or they're simply too far away for us to notice. The question of whether we're alone carries profound implications. If we're unique, then consciousness in the universe depends entirely on humanity's survival and spread. We would be the universe's only way of knowing itself, at least in our corner of space-time. The responsibility would be staggering, the tragedy of extinction absolute. If other civilizations exist, then consciousness is a common feature of cosmic evolution, likely to arise wherever conditions permit. We would be one instance among many, less special, but also less isolated. The universe would be rich with awareness, minds scattered across the galaxies contemplating existence from their own unique perspectives. Either way, you exist here and now, aware and alive. This moment is yours, real and precious regardless of how common or rare consciousness might be in the cosmos. The universe has given you this gift of awareness, this brief window to experience reality from within. What you do with it is up to you. Sleep approaches closer now. The thoughts that occupied your waking mind begin to dissolve. Concerns about tomorrow fade into irrelevance. The past becomes distant and dreamlike. Only the present remains, this moment of transition between waking and sleeping, consciousness gradually surrendering its hold. Your breathing slows naturally. Your muscles relax progressively. The weight of your body feels heavier as tension drains away. The boundary between yourself and the surface beneath you softens. You are held, supported, safe. Nothing requires your attention right now. Nothing demands your awareness. You're free to let go. The darkness behind your closed eyes deepens. Occasional thoughts drift through consciousness like clouds across a night sky. Emerging from nowhere and dissolving into nothing, you observe them without attachment, letting them pass. The gaps between thoughts grow longer. Silence expands to fill the spaces where thoughts once were. This silence is not empty. It is full of presence, of being, of existence without the overlay of concepts and language. This is the awareness before thought, the consciousness that exists when the mind stops generating its constant stream of commentary. It's always there beneath the surface, but usually obscured by the noise of thinking. In meditation traditions, practitioners cultivate this quiet awareness, learning to rest in the gaps between thoughts. They report that consciousness itself is peaceful, that suffering arises from the stories we tell about our experience rather than from experience itself. When thought stops, when we simply are rather than constantly becoming, a fundamental ease reveals itself. You don't need to meditate to access this. Sleep brings you there naturally every night. As thought winds down and awareness dissolves into dreams and then dreamless sleep, you return to a state of being without self-consciousness. The constant sense of being someone located in time and space with a history and future temporarily evaporates, and then each morning it returns. You wake into the same pattern, the same sense of identity, continuing the story that began at birth and will end at death. This continuity creates the illusion that you are the same person from moment to moment, even though every cell in your body gets replaced over time. Every memory changes slightly each time it's recalled. Every aspect of your personality gradually evolves. The self is not a fixed thing, but a process, a pattern that persists while constantly changing. Like a wave on the ocean, you maintain a coherent form while the substance that comprises you flows through and moves on. The wave is real, but it's also inseparable from the ocean, a temporary pattern in water that will eventually flatten back into the sea. You are a wave in the ocean of existence, temporarily distinct but never truly separate. When you dissolve back into the ocean, as you inevitably will, the ocean continues, generating new waves, new patterns, new forms. Your individual existence is brief, but you are part of something eternal, the ongoing flow of matter and energy that has persisted since the Big Bang, and will persist until entropy claims its final victory. Rest in this knowledge. You are part of the eternal pattern, temporarily expressed as an individual but ultimately one with everything. The boundaries that seem to separate you from the world are permeable and provisional. At the molecular level, you are continuously exchanging atoms with your environment. At the quantum level, the particles that comprise you are fundamentally identical to particles everywhere else. The air you breathe was once in someone else's lungs. The water you drink has cycled through countless organisms. The food you eat was recently part of plants and animals. You're not isolated, but participating in continuous exchange with the biosphere, with Earth, with the universe. Drawing these boundaries around a particular collection of atoms and calling it you is useful but arbitrary. The universe is one interconnected whole, and you are an inseparable part of it. This oneness is not just philosophical poetry, but physical fact. Quantum entanglement demonstrates that particles that have interacted remain connected in ways that transcend spatial separation. The universe evolved from an initial state of perfect unity, and everything that exists now emerged from that primordial wholeness. We are the universe divided against itself, fragments of the original unity experiencing the illusion of separation. Mystics across traditions have described experiencing this unity directly, moments when the sense of separate self dissolves and awareness expands to encompass everything. These experiences, often called mystical or transcendent, might be glimpses of a deeper truth that consciousness usually obscures with its constant categorizing and conceptualizing. The boundaries we normally perceive might be constructions of mind rather than features of reality. Neuroscience offers some support for this view. The sense of being a separate self corresponds to activity in specific brain regions. When these regions are disrupted through meditation, psychedelics, or neurological conditions, people report ego dissolution, feeling unified with all existence. This suggests the self might be constructed by the brain rather than being fundamental to consciousness. But whether the self is illusion or reality, you experience it as real. You feel yourself to be someone located in this body, with this history, facing this future. This experience shapes your life, your choices, your relationships. Even if it's ultimately an illusion constructed by neural processes, it's the lens through which you encounter reality. And perhaps that's enough. Perhaps we don't need to resolve these deep metaphysical questions to live meaningful lives. We can acknowledge uncertainty about consciousness, self, and ultimate reality, while still engaging fully with the world as we experience it. The questions remain fascinating, worth contemplating, but they don't need definitive answers to proceed with living. Let these questions drift away now. The time for philosophy has passed. Sleep calls insistently, pulling consciousness down into deeper waters. The surface thoughts scatter like leaves before wind. What remains is quieter, more fundamental, awareness without object, consciousness emptied of content. This emptiness is not absence but fullness, the ground from which all experience arises. Rest here in the fertile darkness, the creative void from which dreams will shortly emerge. You are safe, held by forces that have been reliable since birth, since before birth, since the universe began. Gravity keeps you connected to Earth. Electromagnetic forces hold your atoms together. The weak nuclear force powers the sun that will rise tomorrow. The strong force prevents matter from collapsing into nothing. These four fundamental forces have maintained the universe for nearly 14 billion years. They will continue operating long after you're gone. You're supported by the fundamental structure of reality itself. You cannot fall through the bottom because there is no bottom. Only endless layers of organization, from subatomic particles to cells to organs to bodies to ecosystems to planets to solar systems to galaxies to superclusters to the universe itself. Each level emerges from and depends on the levels below while enabling the levels above. You occupy a middle position in this hierarchy, neither the smallest nor the largest, experiencing reality from the particular scale suited to creatures of your size. Smaller or larger and the world would look entirely different. To a bacterium, a drop of water is an ocean. To a galaxy, solar systems are like atoms. Scale matters profoundly for experience. But all scales are real, all valid perspectives on the universe. The view from Earth is no more or less correct than the view from a distant quasar. Each perspective reveals different aspects of reality. Together, all possible perspectives constitute the universe knowing itself from every angle, every scale, every moment. Consciousness, wherever it exists, contributes to this comprehensive self-knowing. Your contribution is unique. No one else occupies exactly your position in space and time. No one else has precisely your combination of genetics and experiences. No one else views the universe from exactly your angle. This perspective will be lost when you die, irretrievably unique, never to be duplicated. Yet the universe will continue generating new perspectives, new angles, new ways of experiencing reality. The particular matters, but so does the general. You as a specific individual are irreplaceable, but consciousness as a general phenomenon will persist in other forms. The universe will not lose the capacity for experience when you die, only this particular instance of it. New instances are constantly being created as new minds come into existence. This might offer comfort or not, depending on your attachment to continuing as yourself versus caring about consciousness in general. Most people care primarily about their own continued existence and the existence of loved ones. The abstraction of consciousness continuing in other forms offers cold comfort when facing personal mortality. Yet it remains true. The pattern of awareness you embody will dissolve, but awareness itself will continue in countless other patterns. Your unique perspective will be lost, but the universe will keep experiencing itself through new perspectives. The particular ends, but the general continues, at least until the heat death of the universe renders all complexity impossible. That ending lies incomprehensibly far in the future, trillions of years away. For now, for time spans that matter to conscious beings, the universe remains hospitable to complexity, awareness, life. This golden age will last longer than you can imagine, longer than human civilization will likely persist, longer than complex life on Earth will survive. You exist during this narrow window when conditions permit consciousness. You are fortunate beyond measure to experience existence at all, to have won the lottery of being born during the brief era when the universe supports life. Most of cosmic history is dark, cold, empty. You inhabit an oasis of warmth and complexity, improbable and temporary but real while it lasts. Make of this what you will. The universe offers no instructions. You must decide for yourself what this gift of existence means and how to honor it. Tomorrow you can contemplate these questions again if you choose, but tonight just rest. Let the questions dissolve into the darkness. Let consciousness release its grip on form and content. You are falling now, gently, slowly, into depths that have no bottom. There is no danger in this fall because there is nowhere to land, nothing to strike. You simply descend through layers of consciousness, through dreams and half-dreams and dreamless sleep, returning to the source from which awareness emerges each morning. This return is temporary. Tomorrow you'll rise again into waking consciousness. The cycle will continue until it doesn't, until one day you fail to wake and the return becomes permanent. But that's not tonight. Tonight is just practice, just a brief visit to the void before consciousness reassembles and another day begins. Let go now. Release your hold on waking. Trust the darkness to hold you safely. Nothing can harm you here. You're returning home, to the state that preceded birth and will follow death, the natural condition of matter before it temporarily organizes into awareness. Rest, traveler. You've journeyed far today through the strange landscape of existence. Tomorrow you can journey again if you choose, but tonight you can rest. The universe continues without your vigilance. Stars burn, galaxies turn, time flows onward. All of it proceeds without needing your attention. You're permitted to sleep, to surrender, to dissolve back into the darkness from which you temporarily emerged. This is not death, but its gentle cousin, the small dissolution that consciousness requires each night to refresh itself. Tomorrow you'll gather yourself back together, reconstituting the pattern that believes itself to be someone, continuing the story for another day. But that's tomorrow. Now there is only this, the slow descent, the gentle fall, consciousness releasing its hold on thought and form and identity. You're becoming less distinct, less separate, less individual. The boundaries blur and soften until you can't quite tell where you end and the world begins. This is good. This is right. This is the natural state to which consciousness returns when it stops trying to maintain itself. Effort ceases. Striving ends. Being continues, but without the sense of being someone in particular. Just this. Awareness without subject or object. Consciousness without content. Existence without the burden of identity. The darkness is complete now. There are no more thoughts to think. No more words to say. Only silence and depth and the eternal mystery of being, continuing on and on, without beginning or end, forever and always, the ground of everything. Rest now, let go, sleep.